governance and strategic uses. ISRO's microwave remote sensing payloads like synthetic aperture radar for ARISAT-1 and Chandrayaan-2 orbiter, scatterometers for OceanSat-2 and SCATSat, altimeters and hazard detection and avoidance processing systems for lander, to name a few among the long list. He was also responsible for the design and development of real-time data processing techniques, user receivers for indigenous Navig satellite and SATCOM hub earth stations, and user terminals for mobile, broadband, and high-throughput communication satellites. He has also served as Deputy Director, Microwave Remote Sensing Area, and SATCOM and SATNAP Advanced Application Areas, and Associate Director of SAC, and provided leadership and direction in the developing and strengthening space infrastructure, its applications, and many state-of-the-art technologies. He has made considerable effort in popularizing and proliferating usage and applications of indigenous navigation technologies like Navig, Gagan for commercial, governmental, and strategic use. He is an advocate of outreach activities related to Indian space program. He has mentored and designed world-class courses on satellite communications and global navigation satellite systems under the aegis of United Nations Center for Space Science and Technology Educations for Asia and the Pacific. He has published more than 175 technical papers in various national and international conferences and contributed significantly in more than 225 technical reports of ISRO. He has represented ISRO and India at various international forums like in Austria, China, France, Germany, Israel, Russia, Singapore, South Africa, United Kingdom. He is an active and contributing life member of many professional societies like Indian Society of Remote Sensing, Indian Society of Geomatics, Astronautical Society of India, and Indian Society of System for Science and Engineering. Presently, he is serving as National President of ISRS Executive Council and Vice President of ISSE Ahmedabad Chapter. His significant contributions has been recognized by ISRO by bestowing Individual Merit Award in 2010, Team Award in 2012, and Performance Excellent Award in 2018 on him. With this small introduction, I hand over the virtual podium to you, sir. Kindly take over.
Everybody. Thank you, Dr. Chandrakant, for a very detailed introduction. In fact, it is said of George Bernard Shaw that his dramas used to be smaller than his preface. So something I hope it doesn't land up that way. Thank you once again for inviting me for this inauguration of this workshop, as well as a chief guest, and deliver this inaugural keynote address. I thank IEEE MTT AP Bangalore Chapter, as well as IEEE Aerospace Electronics System Society and your India Council members, all the members, participants of this workshop, for inviting me for this workshop on advances in electro-optics and photonic system simulation in aerospace and defense. And once again, I thank Dr. Punit Kumar Mishra also for being the catalyst in these activities, and also for inviting me here. So once again, I thank all of you for being kind enough to tolerate this delay. Also, I had been held up in some other seminar today morning, since morning in Vadodara. So thank you all. And as has been said, this is a very apt occasion to initiate some of this activity related to photonics. And today I'll cover some of the aspects related to quantum technologies as is being applied in Space Application Center and all across the other ISRO centers as well. How we are embarking on this particular quantum communication and other associated technologies. So, but before that, today, some of you may remember, especially my Bangalore friends, today is also a very important day for all of us, because GSAT 8 was launched in 2011, on this date, 21st May 2011.
Yes.
And GSAT 8, we know, all of us know that it carried our Gagan payload also.
Correct.
And then afterwards, it was followed by our NAVIC systems and all. And NAVIC, Gagan, all these things, they have also a great usage of this quantum key related aspect. So I'll cover some of the aspect where we can utilize this quantum technology, and navigation could be one of them. So in that sense, and since GSAT 8 being very important satellite for our missions, and in fact tomorrow, 22nd May, we had launched RISAT 2B, 22nd March 2019. So once again, very important, because such radar satellites are also a key user of some of these quantum technology, especially because for strategic users and all. So when we encrypt the data, to decrypt it, we need that public or private key, and these keys can be transmitted with these quantum technologies. And once again, these are newer technologies, advanced technologies, and lot of other technology development it will usher into with these following up of these particular technologies. And I would again like to emphasize that it is always said that nothing is more powerful than the idea whose time has come. And this quantum technologies, photonics, all these things are the ideas whose time has come now. And it is now time to embark on all these new technologies. And similarly, nothing is more expensive than a missed opportunity. It is said in Bhagavad Gita. So same way, if we, all of us or some of us miss out this opportunity of working on this particular domain of technologies, then we'll rue that we have not taken up at a right time all these developments. And all of us know that India missed out this microelectronics revolution. So today we are struggling to get electronic components. And of course, due to this pandemic and all, there are delays in deliveries and all that. So foundry technologies, microelectronics, all these things, we are dependent totally on European as well as American sources. So considering that these are the technologies, photonics, quantum, and all the other associated activities, which we should not now miss out these opportunities, and we should begin all these developments at the right time, even though we may not have many of the what we call the ingredients to feed into or develop some of these aspects. But if we don't start, we will never acquire those technologies. And we are learning it in a very hard way in our space business. Now, right now, many of the things we are making indigenous, and it takes its own time. Of course, any technology will take its own time. So today is the right time now to embark on this type of photonics and quantum technologies. And I must compliment all of you and your Society office bearers of IEEE as well as IEEE MTT, AP, Bangalore Chapter, and all these people for rising to the occasion and organizing this workshop related to electro-optics as well as photonic system, because electro-optics is a front end of all our quantum technologies as well. Of course, for our sensor development, as Puneet mentioned, LEOS as well as SAC had been very active in developing all these sensors and associated technologies. But this quantum related aspect also, they will feed into those developments as well. So all in all, we are now at the threshold of beginning this new era of communication, which will involve all these photonics and quantum technologies. As all of you know, and with LEO constellation and with the internet through satellites and all these things coming up. So these are exciting times where all these technologies will find its usage with the advent of 6G, 7G, where satellite components are also going to be a very important element, unlike 4G and 5G, where terrestrial networks were dominant. So 6G and 7G has a lot of satellite component as well. So they will feed into all this development also. So as I said, these are now the right time to work out on these new technologies. So let us work on that, and I urge all your members, all my colleagues in ISRO, as well as other institutes of government, as well as private industries, in India, to especially embrace these particular new technologies and work out the roadmap for all these activities. So with this, shall I begin my presentation?
Yes, sir. please.
So as I was told, quantum technologies for space application. So it covers some of the recent advances in satellite-based quantum communication, which ISRO has taken up, and with the Space Application Center at Ahmedabad taking the lead, along with all my other centers in ISRO, as well as other autonomous bodies associated with this DOS, like PRL and other people, and all our other centers like URSC, Sriharikota, SHAR, as well as LEOS, and many others who really want to work on these technologies, because as I said, this is just the beginning. So we have many things to cover in these technologies. So let us have some look at what all are the technologies needed, and how photonics, optoelectronics, optical sensors, they are going to play a role into these technology developments, and how ISRO can work on this and take a lead in our country, because all of you know that Government of India also is giving a lot of impetus to this activity related to quantum frontiers. So in any communication, as George Bernard Shaw said, the single biggest problem is the illusion that it has taken place. And in this particular case of quantum communication, we deliberately try to introduce confusion in the sense that we try to encrypt it and try to transmit the key in such a way that eavesdropper or nobody else will know it. It will be between a transmitter and receiver only. They only know that the communication has taken place. So let other people be confused with this illusion. So some of these topics which I'll be covering, quantum key distribution related thing. Before that, a brief overview on what the traditional way we have been doing communication. Space communication, all of you know, it started, and ISRO's goal was that we want to use technology for man and society, which was the vision given to us by Dr. Vikram Sarabhai, incidentally, who belonged to our place here in Ahmedabad. And we started with this satellite instruction TV experiment. We celebrated sometimes back the 40 years of this site experiment, where 2,400 remote rural villages were put together, stitched together as the largest mass communication experiment. We had American ATS-6 satellite and broadcasted these TV programs. And you can imagine on those days, 75 to 77 time frame, when electricity itself was a luxury in our country. It was not available. Even today, many of our villages are devoid of full-time electricity. So on those days, 50 years back, we tried to connect them with this experiment. So it was really a remarkable activity taken up by ISRO, where many of our ISRO centers participated with, of course, Ahmedabad Center taking the lead. And this was followed by, since we had a very great ambition of having our own communication satellites, and we gave the order for our first series of satellite INSAT 1 series to Ford Aerospace, where many of our then ISAC as well as SAC engineers, they went to USA and participated in design as well as testing part of that. In between fabrication and all other assembly, all these aspects were taken care by Ford Aerospace, but our teams were involved in design and testing. And so this was that as a precursor to this INSAT 1 development, we took up this satellite telecommunication experimental project STEP during 77 to 79, where we tested how this communication experiment can be done with a satellite technology. So disaster warning system, radio networking, transportable terminals like VSAT. Those days there were no VSAT, they were bigger terminals, but still we did the two-way communication, one-way communication. All these experiments were conducted so that people get the feel of how to utilize the satellites. So this was all the initial days where communication we utilize. This is Space Application Center. This was the only building in this part of this Ahmedabad. Those days it was all a forest area, and in this forest, this one building stood up. This was the first Earth station of our country, Ahmedabad Earth Station. And today we have a plethora of earth stations everywhere across the country, but this was our first earth station in the jungle area. And the antenna you are seeing, a 14-meter diameter antenna, which was built by, then it was called Nippon Electric Company, which is nowadays NEC Japan. They built this 14-meter antenna on the order given by our teams those days in 67, 69 time frame. And incidentally, we completed almost 50 years in 2019. Of course, we forgot to celebrate those 50 years of event. But I am very pleased that URSC has been celebrating this year 50 years, and same way SAC is also planning, because as a center we came up in 1972 as a space application center, and Professor Yashpal, whose picture you are seeing in the earlier slide, he was our first director of Space Application Center, he was in TIFR and he took charge in 1972 as the first director of Space Application Center. So to commemorate all these events, we are thinking of planning this celebration this year. And I'm also happy, as I said, that URSC also completed its 50 years of doing satellite development. And this is our first heritage antenna, and right now it has no use, but still we have kept it as our heritage value. And today SAC looks something like this. We have 2 more campuses away from our main campus here, where I'm sitting right now. The other 2 campuses are in Bhopal, which is 7 kilometers away from here. And of course, we also have DECU unit in our campus. Of course, it is a separate unit, but it is almost our sister concern and part of SAC only, Development and Educational Communication Unit. And it has unique capabilities and role to play. They do all these, our documentary and other animation developments. Of course, they do the telemedicine, tele-education, all those experiments, and support operational and other maintenance aspects. Plus, they also have a role in doing what we call a social research. So they give us very important feedback to many of our ISRO programs, whether it is communication or navigation or remote sensing. They go to field and do the survey and then come back with whatever course correction needed for all our programs. So in that sense, that group's activity is also very important for midway course correction of all our space programs. So it has its own importance. And then you see another small antenna here at Delhi Air Station. So again, Delhi Air Station, as its name suggests, it is in Delhi, but still it is part of our Space Application Center, Ahmedabad. And again, this place has a very heritage importance for all of us, because those days in late 70s and early 80s, our Prime Minister used to go to this place, especially Indira Gandhi ji used to go to this place to address the whole country. Today, sitting in my room or your home, you can address anybody through video conferencing, through internet or any other means. But those days, even Prime Minister has to go to this particular place to address the whole country. So again, it has its own importance. So this is what is saying, and we have a very good exhibition, Vikram Sarabhai Space Exhibition. So when you happen to be in Ahmedabad, please do visit us, see our exhibition and see all these heritage buildings. Plus, we have many things for you to show, because we do a lot of development, payloads and applications, communication, navigation, optical camera system, microwave radar systems. So these are the sensors or payloads which we develop for all these ISRO programs, and also associated applications. So in that sense, I always claim that SAC is a unique center because it is multidisciplinary. As you can see from our human resource, we have hardcore technologists, electronics, mechanical, computer scientists that we have in all our ISRO centers. But apart from that, what makes us different is that, as I said, we have social scientists and various other science people like geoscience, biological science, chemical, physical. So many people, agriculturists, horticulturists. So all these people are also working in our place, doing various sorts of application, whether related to remote sensing, navigation, communication, and many other aspects. And as I said, social research. So in that sense, it makes us more vibrant and multidisciplinary, because we have all type of people who debate and discuss on various major aspects. And quantum communication is one of the area which right now we have embarked on under our communication and advanced technology program. So traditionally, we had been doing this communication payload from, say, I used to say DC to GC, and now we have embarked on terahertz program also. So in that sense, from DC to terahertz, we had been working on various communication as well as remote sensing payloads or technologies to work on. And same way navigation program, all of you know, so I did not elaborate much on that, that we have our own Indian GPS or Desi GPS as it is called. We want to replace GPS wherever we can, and wherever we cannot do that, at least augment it with our own NAVIC system, navigation with Indian constellation. Although initially we used to call it Indian Regional Navigation Satellite System, now it is, Honorable Prime Minister has given a name. In fact, he coined it in Hindi, that why not call it NAVIC? So then we coined this English acronym for that, NAVIC, navigation with Indian constellation. And of course, we had this Gagan payload as well. And as I was mentioning, GSAT-8 is completing almost 11 years in orbit today with this Gagan payload, which is again an important payload. And you'll hear a lot about Gagan and NAVIC in coming days, because Gagan is going to be mandatory, that Gagan receivers or S-bus receivers in all the aircrafts. Of course, new aircrafts always come with this Gagan or S-bus receiver, but the old aircraft still, they are not being retrofitted with Gagan receivers, but that also will happen soon, because government is going to come out with that resolution, that regulation, that all, because in fact today only I was in some function and the chief guest there could not landed almost with great difficulty. He could come to that place in Baroda because his plane got stuck. It was diverted from Delhi to Chandigarh because of the bad weather conditions. So those things will be the days of past, because Gagan receiver will help pilot in takeoff and landing even in bad weather conditions. How and all, we will not debate that, but this is the technology which is going, we are going to hear more about all these things, NAVIC and Gagan, in near future. This was our communication scenario, and now all of you know that, so I did not elaborate. Inside 1, 2, 3, all these series where we got it, we did initially, as I said, Ford Aerospace, followed by indigenous development, but we used to launch it from French Guiana, Ariane space. But nowadays we make our own satellite and we launch it from Sriharikota itself through our GSLV. So we call it GSAT series. And of course, we have now high throughput satellite, MSS satellite. So, and in GSAT 29, we put up optical communication terminal, OCT, which is a precursor to now what we are today going to discuss related to quantum technology. So this is the past, and future is going to be optical, quantum, all these things. And we had been doing a lot of applications. All of you know that broadcast communication, meteorological observation, again from same geo platform, and many development programs like telemedicine, telehealth, or tele-education, and disaster communication during disaster, emergency communication. So all in all, we have good space assets as far as communication is concerned, and a very elaborate ground network to support all these applications. Because this is also very important in any space program, not only space segment, but ground segment and the user segment. These are also the very important element or part of any of these developments. So we have a very elaborate communication network on ground also with Earth stations as well as various sensors. And these are some of the applications and technology: disaster alert, VSAT network all across the country, handheld reporting terminal for our MSS satellite, automatic weather station, which again communicate through our communication satellite to transmit the data and reach at the common place for our IMD to use it for its forecast, tsunami early warning system, cyclone warning system. So all in all, we have a good network on ground as well as our station to support our space segment related to communication. And as all of you know, nowadays we have shifted our focus from the standard traditional band pipe transponders, which used to have 36 megahertz bandwidth per channel. Now that has been per transponder. It is now augmented with GSAT-19 was our first high throughput satellite, where we had these two beams, 4 into 2, 8 KU band user beams to give a total cumulative data rate of 3 Gbps data rate now. And then further GSAT-11, which was one of our biggest satellite till date, built by URSC. And it was a very huge satellite. And again, it catered to almost 12 to 15 gigabits per second of high throughput bandwidth. So these are our immediate past or near future activities where high throughput satellite is going to be the main workhorse of communication. And as all of you know now, we are these are the applications we have envisaged for all these commercial, strategic, societal applications. And as I said, a precursor to our quantum technology was this particular satellite, GSAT-29, where we not only supported northern part of our country, Jammu Kashmir and other regions, as well as Northeast, because these two are the areas which felt neglected. So Government of India decided that why not we have dedicated satellites which cater to communication services in these two areas. So we put up beams for KU and Ka band coverage in these areas. And of course, this was a very unique satellite because we also had QV band for the first time. And QV band is going to be the future as far as traditional communication is concerned. And we also had this optical communication terminal. And for that, we built a ground station, also optical ground station in our SAC campus. And of course, it has a geo imaging camera, GHRC, geo high resolution camera, which gave us 50 meter, 55 meter nadir looking images. So all in all, this was a very high end satellite with many new technologies. So in that sense, many technologies were tested, which as I said, they are going to be the precursor to our traditional communication as well as this quantum and optical communication technologies, which are going to be the main workhorse in future or near future. So in that sense, it was a very important satellite, and we succeeded almost in all these activities which we did. Of course, we are still struggling with sending this GHRC data through our optical link, although we could establish communication between our ground station and the optical terminal. And that is going to be the challenge in quantum also. That's why I'll try to highlight that, why I'm putting this, because this is going to be a real challenge. And this was from geo satellite. And when we are talking of quantum communication, we are going to have LEO satellite. So you can imagine a fast moving satellite, and we need to do communication from satellite to ground station or between satellite to satellite. What all challenges we are going to face when we embark on a space-based quantum communication. And this is the ground station which we have built in our SAC campus. And of course, recently when Chairman ISRO was here, we took him to this building, this ground station, and showed him various optics as well as technologies which we have developed. And of course, as I said, we could locate GSAT-29, we can do some beacon transmission and establish communication link, but still we are struggling with getting those high rate data communication in a sustained manner. From GHRC data we want to send from satellite to ground station and vice versa. But we are still far off. We're still struggling. Where is that beam, that elusive beam of optical terminal, which will help us to achieve 1 gigabit per second or at least few hundreds of megabits per second. So because this is going to be the technology of future and a very important technology for quantum communication. And of course, as I said, the whole world is now moving towards, all of you have heard about Starlink, OneWeb and all these things, where people are going for LEO broadband constellation, internet through satellites. And that is going to be the norm in India also. Shortly, ISRO is also going to set up its own constellation, of course, in a public-private partnership mode, because government cannot fund all these 150 satellites which we are planning to put up. So some private user will come up, service provider who will take up this challenge, and then ISRO will build the satellite and then transfer this technology to do the production part of it. And that way we can cover the whole country. And of course, once LEO satellites constellation is there, it can cover the whole world. So then only it will become viable cost-wise. So because we need to put up gateways in respective countries to provide communication. And as I said, putting satellite is not the end of the story. You need an elaborate ground network. So gateways will be required in each country where you want to provide these broadband services through LEO constellation. So again, these technologies are getting developed in SAC and many other places. So all in all, ISRO has been involved in all these technology developments. Although we have not put up this LEO broadband satellite, but lot many technology developments are taking place in SAC, URSC, and the other stakeholder centers. And this is going to be future, because communication, navigation independently we had been doing, but the combination of that, using both navigation and communication for governance, development, and all the other commercial applications. So that is going to be the future or near future, or it has already started, whether it is railway tracking or coastal surveillance, where boats sub 20 meter or bigger boats are being routinely tracked, so that something like Bombay don't happen again and again. And same way we have fishermen being aided through our messaging receivers. Again, all these communication and navigation combinations activities we have been pursuing. And of course, Gaganyaan is going to be another area where all these technologies will be useful. Right now, we are putting up 2 IDRSS satellite, which will ensure us 100% communication with support from other ground systems. But again, this communication is right now not encrypted or not secured in that sense. If somebody wants to hack it, somebody wants to eavesdrop it, it is possible to do that. So in future, when we make this communication encrypted, or it has to be more secure communication between the crew and ground system. So again, quantum communication is going to be very important, because 100% crew communication is necessary in any manned mission. And as I said, with 5G, 6G, and future 7G, and all these challenges coming up, so apart from our traditional network, satellites are going to play a very important role in 6G and 7G. Now coming to this quantum communication, what is so great in this communication? We had been doing communication last so many years. The difference is that now everything, earlier we used to have analog data, all type of communication. Now everything is getting converted into data communication. Even voice also we convert into data and then do data communication, and then again come back to the analog domain. So where data is involved, security is very important. So again, security will have its own implications. As I said, right now encryption methodologies are being used to implement these security provisions in data, because data is going to be, as they say, next oil. So that is going to be very important security aspects. And then what is the issue? The issue is right now some of the encryption algorithm like AES and all, they appear to be very quite robust enough, and it may take some months or years to break it up. But as I said, with quantum technologies coming up, so it is not only quantum communication or photonics and other things come up, but quantum computers are also going to come up. So how these quantum computers are going to change the scenario, we'll see that. And before that, quantum frontiers have been identified as one of the very important missions in Prime Minister's Science, Technology and Innovation Advisory Council also, which is headed by the Principal Scientific Advisor to Prime Minister and Government of India. He is chairing this council, and where our Kiran Kumar sir is one of the members, and there are members from different domains. So some 8 to 10 members are there, and these 8 fields have been identified where quantum frontiers, AI, ML, all these things are very important technologies which they have given priority for implementation. And the importance is quantum frontiers will cover, as I said, quantum communication, quantum computers, quantum radar, and all the sensing technologies. And there is a national mission for quantum technology and applications set up, and almost all the departments of Government of India are working in some way or the other to implement or to develop quantum technologies or use it. And its importance is that, like our Gaganyaan program, which almost involved 10,000 crores of budget, in same way, this quantum frontiers also government has allocated something like 8,000 to 10,000 crores for developing the quantum frontier technologies. So in that sense also, this is going to be very important activity as far as our country is concerned. So, and we hope and we surely wish that ISRO takes up lead into all these activity related to quantum frontiers as well. So this shows its importance and as I say, quantum communication, various material development where photonics, optoelectronics will come into picture, quantum sensors, quantum cryptography. So it opens up a lot of challenges, not only for ISRO people, that is one part, being a research organization and actual implementing agency, but for academia as well, students as well, students like those, all of you who are member of IEEE and various other forums, academia, industry, researchers, students. So it opens up lot many activities, whether it is algorithm development or technology development or sensor development and various aspects related to their implementation, applications. So all in all, it is a very exciting area to work with. Now coming to the activities which are happening in the world, most of you are well aware, but just I have listed it. It is all available in public domain, so we will not spend too much time. Is what this slide summarizes is that almost these activities have been going on since last almost 2000 onwards, although I have shown it from 2005 to 2025 time frame. So these 2 decades are going to be the what we call the consolidation part of building all these quantum technologies. People have demonstrated various algorithms, protocols, did some communication in lab from one transmitter to receiver or vice versa. Similarly, from one room to another room, from satellite, within the satellite itself, from satellite to ground, like Spooky experiment by Singapore, Japan, China, they had some sort of communication experiment. So these are the countries who have taken the lead. And of course, some of the European countries like Germany and Spain, they have also worked on them. ESA is again funding many of these activities. And what you can see at the bottom is some of the activities which have been planned related to this quantum key distribution or free space communication related activities by various countries. And of course, in ISS, CQE, NASA has planned up again an integrated entangled photon source experiment, something similar to which our TRL team has developed quantum entangled source, and we have tested it with our SEC system for doing the free space communication in January. And the same way, we are planning again to set up some of the experiment setups in our PS4 platform in LEO satellite, as well as our technology demonstrator TDS satellite in GEO. So all in all over the world, as you can see, many activities have happened, as has been shown on top. At the bottom, many activities are happening in various European, American, as well as Asian countries related to these activities. So it is the, as I said, we don't have to, it is the idea whose time has come. So nothing is more powerful than idea whose time has come. So this is the idea which is going to catch up, and we shouldn't miss this bus. So it is, as I said, right time to embark on all these activities. These are some of the missions. MISIAS is the very well-known one from Chinese Academy of Science. So these are the payloads. So you can see the way we are building our camera sensor, optical sensor. So it looks something similar to that, because the front end remains more or less same, similar to that. So, and Chinese had been taking lead as always in many of these technology development activities. They have achieved around 1 to 10 kbps of data rates with a single photon source and entangled photon, of course, in bits per second. So that is going to be the real challenge. Of course, many of these things are not well authenticated. People are claiming, but we don't know whether really it has happened. Socrates mission from Japan. Spooky is the recent one from Singapore, National Institute of Singapore. So all in all, lot of things are happening. And as far as the basic activities concerned, quantum key distribution, as I mentioned, we want to develop and distribute this public or private key. So that is the way right now it is being physically sent from one place to another, or it is sent to the same channel where we are transmitting the data. But as you can see, the eavesdropping by adversary is going to be the major challenge or the major bottleneck in this sort of transmission. And if you all send it physically, then sending the physical mechanism, sending a person there from one place to another. So it has its own associated issues related to that. And then we have symmetric key or asymmetric key, where the public-private combination of key are utilized to again enhance the overall security level. So these are all proven technologies. And as we can see, classical right now, many encryption algorithms are available, like AES and modified AES and many other good ones, which many of you may be well aware of. I am not an expert on cryptography, but these algorithms are available, which are sufficiently robust enough. It may take years to break these these keys. So that way we are secure. But as you can see, say for example, RSA 2048 key, it may take trillions of years to break by simpler computation. But as I said, now we are embarking on a quantum era where quantum computers are going to be the order of the day. So that the day is not far off when again we'll be back to square one as far as the technology improvement is concerned. And then again, it is very easy to break all these things which could have taken years to break with the current level of cryptography. Of course, it is quantum bits versus classical bits. All of you know that logical, we work in data domain, logic domain, where 0 and 1s strings are there. It is now being converted into alpha beta quantum bits, where it can take up any of the state, whether you utilize the polarization level or the photon polarization or the spin of the electrons, and many all these specific things which can be utilized, where the complexity, exponential complexity of bits 2 raised to n, when you go for n bit solution, is now converted into n raised to square. That sort of difference with the quantum bits. And as I was mentioning about quantum computers, so IBM, Google, and many other technology companies in US and Europe and elsewhere, they had been working on all these quantum computers. We have been hearing a lot about 50 qubit or 10 qubit or 20 qubit quantum computers being developed by researchers, academia, as well as many of these professional companies. So day is not far off, as we can see, that quantum computers will be able to, as just for example, what we were saying, that a 20 qubit technology fellow can, what we used to take number of years, it can be done now broken in 8 hours. That is what the claim is. So this is the order we are talking about with quantum computers. So quantum computers are going to be the game changer as far as computing resources are concerned, and they will again compromise the security aspect. So again, we have to be one step ahead with quantum communication now to do the protect the security, which was achieved with the high-end encryption algorithms. So the solution is this quantum key distribution using photonic communication, where Heisenberg's uncertainty principle or no cloning theorem, all these things, I will not go into the details. So these are the things which are well-known theories which can be utilized, or the entanglement state of the photons, they can be utilized to build in the security aspect as far as cryptography is concerned. So these are some of the technologies and the devices like polarizer, Faraday rotator, all these things which can be utilized to implement the polarization conversion to make it a polarized photon. So your logic bits are converted into the qubits or photonic polarization. So again, it will work like an optical filter that will let light waves of a specific polarization to pass through by blocking light wave of other polarization. And that way you try to do the key distribution and then decryption at the receiver end. So now as far as quantum communication is concerned, so again, classical communication is, it should be very clear to all that quantum communication doesn't mean that classical communication will not exist. The classical channel has to be there for doing the normal communication, where you will encrypt the data and send it through a classical communication channel, whether it is a fiber optics channel through landline, or it could be the traditional RF link through satellite or free space communication through microwave. So that is going to be there, but there will be an additional quantum channel which will work, and mostly right now it will be working through this photonics or the laser communication, where right now the challenge is to take care of the ambient noise and the atmospheric absorption and other aspects related to attenuation. So mostly this communication will happen at night only, where the ambient noise is less. So this is going to be again a challenge, how to ensure communication or try to implement communication during daytime also, so that we have a good level of communication with good bit error rate. So this is going to be the quantum communication, a classical channel coexisting with a quantum channel. So that is the difference as far as communication scenario is concerned. Then there will be different quantum protocols. As I was mentioning, there will be a weak coherent pulse, or which we call a single photon source, which can be utilized to do communication, or the single photon based protocol, or data transmission. And same way we can have an entangled photon based protocols like BBM92 or BB84 for single photon source, and there are various variants of that. So that again, it also opens up many activities for academia and students and researchers to develop different algorithms and protocols, which will help us to utilize the uncertainty principle and entanglement to implement these various protocols, and then use it for encryption as well as decryption. So this is, for example, this is BB84 protocol, where our logic bits are converted into these photon polarization basis, then they are transmitted, then they are detected, and this detection could be right or wrong, as a kid, because this is dependent on the photons being transmitted. The photon may get absorbed, lost, and then they may not be detected in the right manner. So like your normal communication, where BER is the deciding figure of merit, same way here we have QBER, quantum bit error rate, which will be the basis of any communication quality. So greater than 25 indicates the presence of Eve, means somebody is trying to eavesdrop. So generally the standard is 10 to 11% QBER is good enough to ensure a meaningful communication of your quantum key. So this is one protocol. Same way you can have a BBM92, which is again entangled source. Again, unlike the single photon source protocol of BB84, here you have a reference source as well. So you can put this transmit source and the reference source together, co-located, or what transmitter can exist at one place, and then it will provide reference to both the transmitter as well as the receiver end. So this is how this communication takes place. And again, here entanglement will bring in what we call a more data security, but there has to be, anything has prices to be paid. So that price is the lowering of the data rates. But as I mentioned, in any quantum communication, data rates are not that important, because we are going to transmit only few keys, whether it is your PIN code of your any financial transaction or any other public or private key. So you are exchanging only very few information which are utilized for decoding or decrypting. So data rates are not that important, and with the current technologies, although we are struggling to achieve data rate, but with newer and newer technologies in photonics coming up, we'll end up with a higher data rates as well. So that is the expectation in future. This is how satellite-based communication is going to happen, and ISRO is now trying to conceive, as I mentioned, a satellite-based quantum communication network, where we will have set up a constellation of satellites to cover a larger area. As you can imagine, any one satellite will not be able to serve the purpose. And China, Japan, Singapore, they have already demonstrated space-based quantum communication. So how it will take place? That once I launch a satellite, it will, say in case of single photon source, you have two earth stations. So it will transmit key to both these earth stations. And the second one, it will also transmit the So now, because satellite will have both the keys, anytime this communication takes place, it will generate new key only. Same key cannot be transmitted again and again or generated again and again, because this key growing or key generation happens simultaneously at both the places, at the transmit as well as the receive end. So when it passes through one earth station, it will have one key. When it passes through another earth station, which could be after some time, it will be another key. And when it is communicating with the second earth station, it will also transmit through its traditional communication channel, exclusive OR of these two keys, which all, because it knows what is that key which it has transmitted to the first one. So the exclusive OR of this also will be transmitted through normal channel to the second earth station, so that when communication happens through the normal channel between station A and B, the station B will have exclusive OR of both the first key as well as the second key. So that way it will be able to recover the key of the first station as well. So this way this communication will happen. So without the key being exchanged, automatically the second station will be able to decrypt the data, encrypted data which it is received from the first station. So this is the normal single photon source based communication, where both the number of earth stations will be accessed in sequential manner. While in case of the BBM 92 protocol, where we are using entangled photon source based communication, as I mentioned, in that case there has to be simultaneous communication between the various earth stations. So if we consider a case of two earth stations, then both the earth stations have to be in the visibility of the satellite, and the data will be exchanged. The communication, quantum communication will happen simultaneously between both the earth station from satellite. And this way we can have here in this case, because keys are being stored here in the satellite also, the satellite has to be a trusted node, because if somebody hacks this satellite or take control of this particular satellite, then that becomes a problem. But in this particular case, there is no storage of key on board the satellite, so satellite could be untrusted node as well. So that is the advantage of entangle, as I mentioned earlier also, that you increase the security levels, but at the same time the data rates get drastically reduced, almost a factor of 10. This is going to be the initial payload which ISRO is going to put up in its LEO satellite. So we'll try to cover both the single photon as well as the entangled photon source and try to do experiment. So since I'm using entangled photon source as well as a transmitter, then I will need two channels, because as I mentioned, there we need a reference channel also, and there has to be communication with two channels or the two earth stations simultaneously. So I can invoke, if I'm using a single photon source, I will invoke only one channel to be utilized, because that time communication is taking place with one earth station only. And if it is to be entangled photon source, I will communicate through two channels with two ground stations. This is simpler thing which we have already demonstrated. The other complicated thing is this, what you are seeing at the top, that is PET setup. The PET setup is pointing, acquisition and tracking, and that is going to be the main part. And as I mentioned you about GSAT 29 optical terminal, where we have put up this PET mechanism on board satellite also, as well as on ground station also, but we are still struggling to establish this communication. So this is going to be a real challenge, and we'll need a lot of help from our spacecraft friends to maintain stability of the spacecraft, so that this PET mechanism works. As all of you know, due to the bandwidth or the wavelengths involved, either it is 850 nanometer or 1550 nanometer laser, the beam widths are very narrow, and to maintain within this coverage and pointing on ground station with such a narrow beam, see, the satellite pointing is going to be, or satellite OD and other things are going to be very critical. And of course, you will have a normal RF communication link as well, whether it is KU band or CAP band and all. So this in summary will be the payload which will go into the LEO satellite, and corresponding mechanism has to be put on ground also. So you'll have, as I mentioned, this is a photograph of our optical ground station in our Space Application Center campus, where we have initially started with the 200 mm optics, then we changed it to 300 mm because we were trying to establish communication with the GSAT 29 OCT terminal. As I mentioned, we were still struggling. So right now we have put now 700 mm telescope. The general trend is to have 700 to 1.2 meter big telescopes in this optical ground station. So these are going to be again the major work areas, and where we'll need support from our LEOs as well as ISTREC and other friends at different centers. And some of the sites, after doing the attenuation studies, atmospheric studies, our scientists at SPL as well as SAC application scientists have worked out the most suitable site is Henley in Ladakh. All of you know that Henley is situated at a very height, and the atmosphere there is very clean. And this is going to be where very many telescopes are also being set up there. So Henley Ladakh is going to be the ideal site for our optical ground station for quantum communication, followed by Mount Abu. Mount Abu also we have a setup for our solar observatories there, set up by PRL. Then third will be our Ahmedabad, and last will be Ponmudi. Of course, Ponmudi is at height, but a lot of aerosol and all other contaminations are there. So although it is situated at height, it has, compared to other three sites, it is coming at as a last option. But still, we are considering all these 4 sites for establishing our initial Earth station. And then it will be followed by a ground network, so that there will be many nodes because if you want to implement quantum communication all across the country, which is going to be the scenario in final stage. These are some of the link calculation where we are using right now 785 or 800 nanometer laser. And as I mentioned, it cannot work during daytime. So the communication happens during nighttime. So when we launch the satellite, that also it will happen nighttime. And as you can see, the data rates achievable with all these technologies right now will be less than between 10 to 20 kilobits per second. This was the experiment we carried out last year in March 2021, where we used a single photon source, and from our building number 22 to our sensor building in SEDA, that is building number 38, which are situated with a free space distance of 300 meters with a line of sight distance. So we could communicate using this single photon source and do the quantum key distribution. So initially we established this beacon signal to verify the link, and then that was followed by this quantum communication. So this was the first attempt anywhere in our country to do this using BB84 protocol and a single photon source to do this transmission. We achieved around 250 to 300 kilobits per second. We did text message transmission, then video transmission, then video communication, video conferencing, and picture transmission, JPEG, that sort of communication, and image processing. So all these various aspects were tested with the quantum key distribution. So encrypted data went through the normal channel through Ethernet LAN network between these two buildings, and we carried out the key distribution through this free space communication through quantum. So this, as I said, traditional communication will happen through either landline or through our normal RF transmission, while quantum communication will happen through photonics. So this was the internal block diagram of the setup which we had. So apart from optical front end, we have a FPGA based processing system, and then one more requirement is the critical timing synchronization and time tagging. So that is supported by, we initially used GPS and then converted it to a GNSS receiver, which also utilized our NAVIC signal. So that was also one major achievement, where we utilized our own navigation signal to do the time synchronization to the level of almost 4 to 5 nanosecond. Although initial setup was around 50 to 100 nanosecond, then it was slowly fine-tuned to achieve this by 4 to 5 nanosecond of time synchronization by doing different pulse transmission. So this was that building terrace of building number 38, and we have set up a hut on building number 22, which was the receiver. The transmitter was at this end, and this was the setup at these two places, Alice and Bob, A and B as it is called. So transmitter and receiver, and this was tested when they are situated 300 meter line of sight. So the rates achieved were around 250 to 300 kilobits at 20 megahertz. If we go to around 100 megahertz, we may achieve slightly higher rates, but all in all, again, 100 megahertz will have its own other interface related issues. So this was the video conferencing which we carried out, where we encrypted the camera signal and then transmitted it, then encrypted signal and then decoded it using that. It came up in a lot of newspaper and other thing. And then we did this year when Chairman ISRO was here in January. We demonstrated to him this entangled source, which was developed by our PRL team, because they had been working on this since last 10 years. So you can imagine the groundwork needed to be done. But now these technologies have matured, and any of you who want to start work on the photonics or the optical front end or the source development or detector development. So many options are available now, including synchronization and real-time processing of the final data. So this we carried out in January and demonstrated this entangled photon source based BBF 92 based protocol for quantum key distribution. So this was the setup. As I mentioned, there was an entangled photon source kept at one building, and it could be co-located with building transmitter, and one receiver was put at same place, and these or source could be at third party end also. So that is the choice, the whichever way you want to do this communication. And then there will be communication between building 1 and 2 through these two receivers. So source will give signals to both the receivers, and then communication will happen between these two receivers. So again, same setup was utilized, only the source was different. So instead of single photon source, we use an entangled photon source. And the results, as you can see here, the communication wavelength was same, again 785 nanometer to 810 in that range. And we could achieve around 4 to 5 secure key rate of around less than 2 kilobits. So between 1 and 2 kilobits per second. Again, it was well reported in various sites. So coming to the overall technologies needed. So these are some of the technologies, as I already mentioned. So you need to develop various technology related to optical front end as well as the back end processing, receivers, transmitters, as well as channel modeling for doing the atmospheric studies, attenuation modeling, then timing and synchronization using various GNSS receiver. And then if you want to do quantum radar or quantum sensing, then we will need what we call a microwave photonic source. So we have taken up many technology development programs in my center here at Ahmedabad, and many of these are on the verge of at different stages of completion. And we are hopeful in next 1 year or so, we'll have grip on many of these technologies. Right now, we have used many of the imported components, which we plan to replace it with our indigenous developments. This is one of the other experiment, which, as I mentioned, what Singapore did on its spooky satellite. Something similar we were planning with an entangled photon source of PRL. So we are trying to ruggedize it using our SAC technologies and put it on the same platform in a PS4 platform of our fourth stage of our PSLV rocket, and where we'll do this Hongo Mandel receiver. So we can do what we call a end-to-end loopback testing of transmitter and receiver. So from entangled photon source, we'll transmit the signal, we'll give it to this FPGA-based receiver, which we call it Alice and Bob. Both modules will be implemented in this FPGA-based receiver, and we try to carry out the point-to-point testing on the same platform itself, and then telemeter the signal. So if the whatever key we have transmitted from the transmitter, whether it has reached the receiver properly or not, that we verify, and if it is proper, then we accordingly send the telemetry signal to ground. So the communication with ground is not through optical ground station, but it will only give us telemetry signal that whatever is happening on board has happened correctly. So this is how the first stage, everybody does like this only. Of course, there are multiple opinions whether any meaningful result will be achieved by doing this activity and all that, because some are suggesting, some of our scientists, management people, that why not do it on ground itself? It will undergo all thermovac testing and all those things, and then you test it on ground in lab itself. So that is good enough, like equivalent to testing in satellite. For argument's sake, it is correct, but I am of the opinion that putting anything in satellite and then testing it, it has its own different connotation. So of course, we'll try to convince our management that we can put it there. So this is how it will look like. So in the PSLV 4th stage, we are trying to put this. The payload total weight will be around 17 kg, and it will consume around 15 watts, 70 watt of power, because there are lot many other elements are also there, FPGA based processing and all. So we have worked out all the details and started development also. And if our management is coming, then we'll put it in one of our PS4 satellites in next 2 or 3 upcoming missions. Any of the stage we can do. And then parallelly, we are also putting up a proposal for payload for this geo satellite, where again, it's of course similar one, both single photon and entangled photon will put in end-to-end configuration with loopback combination, where transmitter and receiver will be co-located 2 meter or 3 meter apart on the same platform, and will telemeter the correct communication results back to including QBER and all these parameters which we compute on board itself. So this will be another experiment. This is how the payload will look like for this TDS satellite, which ISRO has already planned, and work has been going on to test various technologies on this. And this is the roadmap. So work was started around 2018-19 time frame. Of course, we were affected by COVID during 2021, but in some way or the other, we continued that. 21, we demonstrated the single photon source free space communication. This year, we did with the entangled photon source, and the plan is that if we could, by 23-24, we test it on the PSLV, PS4 as well as TDS. Then by 25-26, we will have our own quantum LEO satellite. So already planned for 2 LEO satellite proposal has been sent to our URSC Bangalore. So our TMC will examine that, and shortly we'll put it up for government's approval. 2 satellite constellation for verifying this quantum communication with a ground station at Ahmedabad and Abu. That is the way right now we are planning. So this is how it will take place. And as I say, finally this configuration, once quantum communication gets established, it will look something like this. So our station, you cannot put our station in every city. So different cities will be connected for communication, because this financial transaction and network will be needed all across the country. So from the earth station, there will be one master node through terrestrial network will transmit these keys which were received by this. Again, it will happen through photonic transmission only, through photons, but you need repeaters at different end, because the terrestrial communication will go only up to few hundreds or at the most tens or hundreds of kilometers. So after that, you will need a repeater. So this is how the whole infrastructure in the country. So there will be many stakeholders. So ISRO is one of them, providing the space segment and the ground station. But apart from that, you will need DOT, DRDO, and many other agencies to work out the whole network. And the final users will be our banking sector, financial sector, stock market, and all these things. And this is something of interest which is relevant to your workshop. Photonic integrated devices for this quantum technology, they are to be built. So photonics is going to be a very important element, whether it is assembly, fabrication, various new developments to be taken up, various new materials to be involved in doing this fabrication. So various simulation, modeling, all these things to be carried out. Application, I already told, banking, finance, credit card industry, government, defense, our NAVIC receiver for military usage, they will all have to be protected with these encrypted keys. So that key transmission, right now military does it through physical means or through that trusted network. So that has to be converted into quantum communication based system. Challenges are many, as I have mentioned: line of sight communication, pointing, tracking, and equation, PAT is going to be very important. Efficient single photon source and detector development, that is again going to be a challenge. Whether operation can be carried out during daytime, so we have to switch over to 1550 nanometer or that sort of sources. A lot many changes, lot many new development will happen, something like that. And then final one is through having our own satellite constellations in an operational way. Quantum radar is going to be another area where this technology will be directly used. Most of the technologies which we develop for communication will be usable there also. Again, the use is your normal radars which are protecting your borders, where they try to locate any unwanted target or foreign target and try to shut it down. at our border area so that they don't enter our airspace. So, but these traditional radars have limitations. So they are not able to detect stealth target. As you would have seen many times, we get the news that some unidentified object or aircraft from foreign country has entered our airspace without permission. So all these things will be thing of the past once quantum radars are put in place, because they will be able to detect even stealth target also. So that is the beauty of having this quantum radar. But the challenge is, right now we have all been working with the optical photonics detectors and transmitters. But what we will need for quantum radar will be something called microwave quantum radar, that is microwave photonic element. So that is going to be a real challenge, because still now it is only in literature. There is no microwave photon source. So that is again going to be a very, very challenging development as far as fabrication industry is concerned. Some of the experiment people have done in China, Japan and other places, they are shown here, but there is no authenticity about whether really what has been achieved, because of the information is very sketchy, whether they have done it in optical domain or microwave photonic source. So again, that information, China is claiming something, but as all of you know, we have to take it with a pinch of salt. So these are some of the technologies which are going to be relevant for quantum radar. Many of these technologies are common, whether it is communication or receiver or computing. We have initiated some activity in lab by having a transmitter and receiver and trying to do some sort of delay switching to verify the time delay or the delay between two signals. So that way trying to simulate the radar phenomena ranging experiments. And again, using entangled photon source, we try to do that. Please do come to SAC, visit our exhibition, where you'll come to know about many more new activities which SAC has been doing, or the other activities which we have already done about that. It is worth seeing. We have a very good exhibition, as I used to mention. Thank you all. We thank all the seminar participants for all this. Thank you.
Thank you, sir. Thank you very much for a very, very exhaustive and elaborate presentation. I think this is one of the best lectures what we have organized under our chapter as well as AES. And we could see the glimpse of the quantum activities, whatever is happening in SAC. In fact, your presentation started with what SAC is doing, then what are the typical communication payload, remote sensing payload, navigation payload, and then coming to the quantum based payloads and what are the challenges involved, how SAC is dealing with that. In a very simple way, you have explained that how normal bit versus a quantum bit. I think that was the most interesting thing for our participants, being a lot of positive things. Because in 1.5, even though time we have straight, but in I don't think there would have been anyone else who would have covered this topic. This is very, very exhaustive and elaborate topic, but in a short span of 1.5 hours, you have explained almost all aspects of quantum communication. And you have also touched upon the quantum radars, which is going to be a future for any defense application. So I think that is very, very important thing. And I'm really happy to note that by 2025, we will be having a satellite, not one, but in fact, 2 satellites working on this quantum communication. And we have mastered the quantum key distribution technology as well. So thank you very much, sir, for joining us. I know morning onwards, you are really busy. And because of your busy schedule, we were forced to reschedule this. But yes, now I can say that, yes, that reschedulement was worth. And from beginning now, seeing almost 100 participants continuously staying and listening you. So thank you very much, sir, for your time and sharing this very, very important information with all of us and all our members.
Thank you.
So thank you. One question, I think not more than one question. If anybody is having you'll be able to take only one question. So I think there are not much things. So we will now move on to next. Before moving to the next topic, sir, I will ask only one question. This quantum communication, when we talk about quantum satellite and quantum radar, so how you see, even you have rightly said that in microelectronics, we have lost, in fact, 3 decades. I will call it 3 decades of lost opportunity. But how we are positioned globally in this quantum technology, sir?
Yeah, as I said, government has set up this Prime Minister Advisory Council, and NMQTA is the Technology and Application Program. And they've directed all the government departments to give adequate funding for this activity in different domains. So in that sense, that seriousness has been shown, especially at the governance level or government level. Now it is up to the academia and the researchers to take up this challenge and embark on meaningful research and activity. Of course, Center for Sensing has been set up, Sense in IISc. So they've been working. IIT Chennai has again another center of excellence set up, where again government is going to fund it in a big way for all this photonics development. And I hope that many other such we are setting up at SAC, the nanotechnology fab, and same way SSPL and many other DRDO organizations, they are also taking up these challenges and developing some of these photonics and optoelectronics related development. So all in all, various research and government institutes are gearing up, but we were discussing with 1 or 2 other industries also, means commercial sector also, so they are also very keen to set up this, because as I said, financial sector is going to be the most beneficiary of this encryption and this key distribution, because many frauds, cyber crimes, they happen in this sector, finance, stock market and all this. So they have a lot of stake in this particular technology. So many private industries are also coming up. They have shown a lot of interest, and in fact they are ready to fund for technology transfer also. So that way there are exciting opportunities for all the stakeholders. So it is going to come up, and I am sure that we are not going to miss this opportunity, unlike the microelectronics revolution.
Yes, sir. Thank you, sir. And you have also told us I think for the first time, we could hear that we are going to have our own LEO constellation for providing this internet services using quantum communication.
That we have been discussing since long.
Sir, but what is your idea by when we can expect that it will be ready and launched?
Yeah, means what we are proposing right now, again, same way like quantum satellite, 2 satellites, same way 2 or 3 satellite, ISRO Suomoto will take up and demonstrate, so that people have sufficient confidence that technology is available, because it will need active beamforming and many other things. So that technologies we develop, then some player, maybe like Jio, Reliance and many other stakeholders who are the service provider, they can develop that confidence into our capability, and they will come forward for funding. And there had been some discussion already going on through our NCIL for having the private players being a collaborator in this, because government alone is not going to fund, because it will need huge fund, but we'll be building it through COTS component. So that way cost of the satellite, which nowadays a simpler one will cost you around 300-400 crores, will come down to of the order of 10 to 15 crore only per satellite. So, and if it doesn't work, we have to throw it off.
Yeah. Sir, I will take one last question, which is relevant here. Question has been asked that how far we have reached in the development of quantum sources operating in microwave region.
Yeah, microwave, still there is no progress, because all over worldwide, we try to find out and buy the micronic photon source, but still it is only in literature. That is what somebody told. But one or two professors were saying that there have been some developments, the results have been achieved, but it is going to be a real challenge. So somebody who wants to take up that activity is going to be a real worth taking up those challenge. It is still far off as far as microwave photonic source is concerned.
Thank you, sir. I know questions are popping up. We will share and we will get the answers, but now we cannot take more questions. Already sir is having some other assignment as well. So we will be again. Thank you very much for joining us and providing a very, very wonderful perspective. And all our participants, they are really thrilled with the activities, what is happening at SAC in quantum communication. And in fact, most of them, they are writing that they want to participate because you have already invited them. So they want to participate and join the journey of quantum technology in India. Thank you very much, sir. Thank you.
Thank you.
So Mahesh, now we can go to the next session.
Yes, sir. Thank you, sir. And now I request Dr. Ashutosh Kedar, sir, to introduce next keynote speaker, Dr. M. Senthil Kumar, sir.
Dr. Kedar, we are not able to hear you. No, I think we are not able to hear you, Dr. Kedar.
I think he is muted, I think, sir. Can you unmute him, sir? Or can you make him the co-host?
He is already co-host, I think. 1 second. One second, Dr. Kedar. I think I have to. You are supposed to be co-host. Yes. Now you try. You have to unmute yourself. Dr. Chandrakant, can you take over?
Yeah, let me introduce Dr. Senthil Kumar. I just opened his. Am I audible?
Yes, yes. Please go ahead.
Hello, am I audible now?
Yes, yes, Dr. Astos, you are audible.
Yeah.
You can go ahead.
Yeah, sorry. So, thank you all for giving me an opportunity to present my next speaker. So our next speaker is Mr. Senthil Kumar, sir, and he received his Master of Technology in Applied Optics from Indian Institute of Technology in 1990, Master of Business Administration from BK School of Business Management, Gujarat University in 1997, and PhD in the area of Optical Engineering from Indian Institute of Space Sciences and Technology, Thiruvananthapuram in 2014. He joined Space Application Center, Ahmedabad as scientist engineer in 1991. Since then, he has been design, integration,
I think, Dr. Kedar, we are not able to hear you properly. No problem.
Yeah, it's thank you so much.
For various
We are running out of time. Thank you, Dr. Ashutosh. I will start the
Electro-optical remote
presentation
sensing.
because
Currently, is the Group Director of Optical Systems, OSD, and Associate Project Director. You to deliver your lecture. Over to you, sir.
yeah. Thank you so much because we are running out of time. I will start the presentations. First of all, I'm audible now, Dr. Puneet. I'm audible.
Yes, sir.
Yeah.
Yes, sir. You are audible.
Yeah. So first of all, warm greetings to the joint organizer, today's joint organizer for this virtual summit, and also the overwhelming response of online participants. It's a very good evening to all. As a keynote speaker, I understand I have to set a platform or stage for the others regarding this simulation and design tools. In that context, I will make a presentation. I hope that I will complete in 20 to 25 minutes so that others can discuss in detail. So I'll share my screen, my presentations. Hope my presentation is visible.
Yes, sir. Your presentation is visible.
Yeah,
Please go ahead.
yeah. See, this first slide itself, you see that if I had, there was a conference in 1994. I presented a paper in that IIT Madras conference. That time, the kind of presentations I made, I have to use draftsman to draw the certain layouts, and that has to be scanned and put, or it was put in OHP, and what I have presented is. Now the visualization has improved. I could make the first slide itself. I can say that this left hand side is what is the remote sensor, satellite borne remote sensor, what it does, and right hand side you can see this is the imaging telescope. And if you go down, these are the light restrainers which will try to stop unwanted optical noise. And if you go to down left, this looks like a surface. It is nothing but a wavefront which has been simulated. And bottom you can see in that the kind of wavefront, what kind of the spot or image profile will be there. So all this thing I could do it in matter of 20 minutes. This is the simulation and design tools, whatever the advancement which helps us to create all these things. Not only create, to simulate, to understand how the system is going to perform, and also experimentally we validate and we always we revalidate the models. And one more thing I would like to tell, in 1991-92, I used to design with the Genesis software. That this kind of visualization won't be there. We have to only see the numbers. With that, we have to understand how the system is going to perform. On top of that, I will give an example. In 1995, we have launched a high-resolution satellite, which was one among the best civilian satellite in that time frame. So we want to align the system. For the alignment also, this design and simulation tools has been used, that whatever the package I was telling, which does not have I think many of the people knowing that Zernicke polynomial, which was not there. So we have to develop a surface fit using a power series, then convert that thing into Zernicke polynomial using a Zernicke to surface fit convert equations. So with that we have done. And one more thing is, there was a NISA software which used to do a finite element analysis, which used to generate the deformation matrix only. From the deformation matrix, we generate the Zernicke polynomial when we are able to evaluate how the optical system is going to perform. All these things, it's a highly cumbersome, tedious exercise. But nowadays, the packages are, I think, I don't want to name the package, that will come in the later discussion. Now, optomechanical models are environmental effects on the optical performance, all done in one package. So all is integrated. And just I want to quote whatever Director SAC said. Now, the quantum communications will have a front end will be the normal imaging instrument only will play as a communication systems. Then the other ends will be using the photonic device. Now it will be a more requirement in integration of classical system and photonic devices modeling and understanding the performance. So now each and everyone should know that what is the performance they want to evaluate the system. This becomes a mandatory in using the simulation tools. Anyhow, while going, it will come out. So I'll take up what is remote sensing, because I'm going to talk about the design and design and simulation tools for the development of optical system for remote sensing. Remote sensing is the acquisition of information of an object or phenomena without making a physical contact. See, just in COVID time, earlier days when we want to measure the temperature of the body, the thermometer is put under the tongue. But when COVID came, everyone is gone into remote sensing mode only. That IR gun has come, even 1 meter away, they will try to sense the temperature. So this is the one kind of remote sensing in practical thing has happened. However, in our application domain, we want to monitor the crop or earth resources. It's not possible to go to each and every place to monitor take the measurements. In that context, so these remote sensors came as an handy, and the phenomena which we are interested may not be directly coming through the instrument, but it is derived from some other variable. In case of optical sensor, that optical property, if you see as a wave, y equal to a sine omega t, a is the amplitude and omega is the function of frequency or wavelength, then there is a phase time. We normally restrict to amplitude. Since light is a high frequency, so always we measure the intensity, then the wavelength. So we talk about wavelength and the intensity we measure. With that, we will able to tell that the physical or phenomena or earth resources like crop or water resources, we will able to tell how the resources are changing or managing or monitoring is happening. So now remote sensor platforms. So we can have a remote sensing. What we are doing, our eye itself a very good remote sensor. Normally, whenever I give a talk, I always refer to the eye and eye. Eye is the high, whatever human eye is the highly technologically sophisticated remote sensor. So the remote sensor, if you use it in lighthouse, if you go to aircraft platform and we go to satellite, so our monitoring becomes more frequent. That's why that satellite based remote sensing becomes more mandatory for monitoring the earth resources. So in that context, if you see, in that context, if you see an remote sensor, a typical electro-optical system consists of an optical system, which is the front end of any electro-optical system. You can see a detector which converts the photon into electron, which may be a linear or a charge coupled device. And there will be a focal plane electronics, which is used to power the detector and also take out the charges, voltage. So there will be a camera electronics that will do the video processing, and it will be fed to the ground. And all this thing will be contained inside a mechanical element that is called the camera structure or mechanical structure. This all together makes an electro-optical system. However, for today's talk, I will confine only to the optical system, that is the front end of the electro-optical sensor. So now coming to design of an optical sensor for an electro-optical system, these are the primary definitions. Like spatial frequency is the geometrical projection of the system onto the ground or wherever we want to monitor. Then measure. Spectral, that is a wavelength of operations of the optical light we are interested. And temporal can be a like a temporal frequency increases from ground to spatial when we are in satellite platform. However, for the optical definition, that field of view will come into the picture. So temporal, more larger the field of view, we will be covering the place more often. Then radiometric is the digitization of image intensity. Whatever the light received, intensity we received at what color tone or a gray level we want to see. That is the radiometric resolution. So all this thing makes a electro-optical sensor for the remote sensing. Even for our mobile camera also has this kind of performance parameter only. But when coming to the imaging performance metrics, see, normally when we are designing a system, all systems are designed and tested independently. So every system has got a performance evaluation matrix or metric, you can say that. In this, for an imaging system, the performance is measured in terms of modulation transfer function at spatial frequency of interest and signal to noise ratio. The product of this only makes the system behavior. Any one of goes to zero means the performance of the system will go to zero. Even if I have a very good noise to noise ratio, if MTF is poor, then we will not get the image whatever we require to. So this two parameters of this data represents the object space details. Normally, what we are trying to see in the image is what we in the object space, what are the things are there. So this performance parameter is very, very important. So all designs will be confined to all these performance parameters. So now coming to the design of the system, any system design start with study of system specification, selection of design, because mostly now we are fed with lot of knowledge base, and so normally we have to look for the literatures rather than starting from individually. So selection of starting design will always lead to a more productivity and fast turnaround thing. So starting design is very, very important. Then definition of variables and constraints and merit function, because variables and constraint, variable is the parameter, like if you take an optical system, curvature, thickness, spin, all will come as a variables. Constraint is because we are not everywhere we are economically limited. Even the designing of system also, we have to put a constraint to make system smaller or within the space. Apart from that, what are the available material, available parameters, like that we have to constrain. And merit function is the finally we have a target with, we want to minimize the initial performance such that our performance and targeted performance will go to zero. Anyhow, it is minimizing only, we cannot go to zero. So that's why that optimization comes into picture. So we try to optimize, the optimization is carried out on various variables to get minimum merit function. Then after the merit function, so we will get a first cut design. Then analysis or evaluation of system parameter has to take place. If that meets the specification, then only we have to go to next level. And evaluation performance is the performance, not only the optical performance, all system performance or system requirement. Like if you design a system which is having a 0.001 micron changes can affect the performance. Right now, we do not have the material, those kind of material. If we can go to composite, which can give a 0.01 ppm kind of thing. When we go to INVAR, it gives 1 ppm kind of CT coefficient of thermal expansion. So we have to look for a practical system. Then we have to, if those constraints are met, then we have to do the sensitivity and tolerance analysis for environment, for fabrication, because we should not see that the thing can be fabricated only if it is tested. So we should know that what are the systems can be fabricated. Accordingly, we have to design. And if it is a ground-based or terrestrial-based, it has got its own environmental. When we go to space-based, it has got vacuum and radiation. So those kind of environmental sensitivity has to be carried out. If that is okay, then we can generate the fabrication detail. If it is not there, then again we have to increase the variables or change the starting design itself. Again, this cycle will go on. Then finally, we will generate the fab design. Not only the simulation tools ends there. Again, whenever the integration is happening, optical system integration is happening by reverse optimization. Now we have gone from front to image performance. From the deviation from the image performance, we can what are the system is misaligned or still has to be aligned, which can be uh, through the design software we can we can know that. Accordingly, we have to do the optimization or alignment, we have to do it. So this design tools per se, it's not only used for design, it is used for end-to-end till the system is getting integrated and at lab level the performance is evaluated. So now I will go to the typical remote sensors. What kind of systems used in the typical remote sensor optical system? See, normally reflective and cathode dioptric. Cathode dioptric means it uses lens and mirror combination is called cathode dioptic, whereas reflective use only mirrors. So these are the system mostly used for high resolution optical images. So these are the systems, two mirror Cassegrain. Normally, if you see astronomical people, mostly you go for two mirror Cassegrain because the fabrication of these mirrors are all very easy. Then comes a two mirror Cassegrain or Ritchie Christian with the additional optics, which will increase our field of view because our temporal resolution can increase. Then comes three mirror anastigmat. This three mirror anastigmat, it's little voluminous, but it has got a very good performance characteristics, but voluminous which makes the system for a very high resolution. Then comes the all mirrors coarse telescope. This system is used for most of the sub-meter resolution optical system used in orbit across the world. So these are the systems which we have to design. This design tool comes as an handy to design this optical systems. Now coming to the performance parameter, I urge upon each whomsoever doing the design, the performance parameter, we should know that what is the performance parameter. Otherwise, the design will be good, but it will not work what we want intended to do for. So for the telescope, MTF, modulation transfer function. If you see, there is a black and white target. If it goes through the system, it is like an impulse function or a system response, which gets 100%. Let us take this is 100%. Black is black and white is white. When it goes to the system, the 300 counts will be the white and 200 counts will be the background. So the modulation will be 20%. So whenever the image, whenever object is having an 100% contrast, which goes into the system, even the system is designed, the diffraction, that is the theoretical limit, will try to limit the performance of the system. Apart from that, all other design limit, fabrication errors plus alignment errors, which further will reduce the performance at the image end. Then comes stray light. I urge upon each and everyone, this stray light is one of the major parameter. Most of the people do the design taking the MTF, whatever the performance, spot radius, all this into account. But mostly they don't do the stray light, which is an optical noise on MTF, which has to be carried out in parallel with the design. So the otherwise, what will happen? Though the design system is giving a very good MTF, like 300 counts and 200 counts in the black and white, but because of the noise, the difference remains. The difference, what will happen? The contrast will go down. The same, it's a very good imaging system. Because of the noise, it will be performing poorly. So the as such, we have to do a spot radius optimization. Apart parallelly, we have to do a stray light analysis so that our performance can withstand the stray light also, that is optical noise. So stray light analysis and simulation tools are all very important when we do a design for an optical imager. So here we are I want to say that when you have a two mirror system, there always the substitute systems are all like MTF because of obscuration. the spot will spread. So the theoretical limit of the obscuration system will be poorer than the unobscured system. This is the graph it shows. So whenever the obscuration is increased, that whatever the MTF spot will spread because of diffraction. So MTF modulation transfer function theoretically also reduces at the various normalized frequency. That means that is the spatial resolution we are working on. So when we work mostly for high resolution system, we will be using an centrally obscured optical system because of its less complexity as well as moderate compactness. So these designs are preferred. And also when we want to do an high resolution system, so the field of view will be a little lesser. So we will be putting a spacecraft. So in order to meet the high moment inertia, I mean, this is centrally obscured systems are preferred. But however, the centrally obscured system comes with stray light, which is very, very prone to stray light compared to the unobscured systems. Because the stray light directly, some of the lights can reach to the image plane if we don't have this kind of baffles. Baffles are the light limiting devices which is need to be designed in parallel with the performance optimization. The placement of baffle increases the obscuration because whenever we try to put a baffle to reduce the direct light, which will increase the obscuration. So increase in obscuration will come at a cost of reduction in the performance, that is modulation transfer function. So the design of baffles, we have to do an optimal design of baffles, which is we have to design a baffle which will restrict the direct rays and the obscuration shall be minimum so that unobscured imaging rays are not vigneted. If it is a vignette, there is a beam, vignette means there is a blockage of ray, then intensity, that uniformity from center to outer images will vary. So we have to preserve the uniform intensity across the image. For that, the baffle design also in such a way that it should not vignette the unobscured seen rays. So this is the thing. These are the two mirror telescope. Because why I am showing all these things, these are the design tools or simulation tools which makes handy to visualize the thing. Rather, initially we visualize the problem, then we go for the qualitative and quantitatively we will be doing the studies. So you can see that this is the two mirror system. You can see the entire image field is flooded with the stray light. So when if the system is designed perfectly, when we don't have the proper light stray light controls, this entire image is flooded with the noises, optical noises, which is not non-seen rays. So in order to that, we have to design stray light baffles. If you go through the earlier literatures, there are many stray light analysis packages are there, but they cannot be used for design. There is no direct method of baffle design with available optical design packages also. This is the 1998 Smith made a statement in a journal. It's a applied optics journal. So earlier days, what they will do, they will use a ray, just a graphic method, like draw a ray using a graph, and they will try to design the light stop baffles. But those things are all valid for a narrow field of view. But whereas we are for our applications, we want always cover a larger swath. It means we want to cover like 100 kilometers, 200 kilometers like that, so that our revisit or repeatability of seeing the same spot will be high. So our field of view will be more. So these kind of designs are not appropriate when we go to larger field of view. But initially it was told that there is no analytical method of baffle design. However, Hales has formulated an analytical method by solving second order and fourth order polynomials. He could show that we can design a baffle using an analytical method. However, all these methods are limited to narrow FOV Cassegrain system because they are taking some kind of a system, more nominal system, telescope system they are taking for the designing baffle. However, in later period, what happens, there are a lot of design, stray light tools have come. with the tools, they will brute force method. They will try to put that baffles or obstruction at various points on the telescope and trace the thousands of rays. Then they will analyze. So it is like a blind kind of thing. We put stops here and there, and trial and error. We will try to design this thing. This was also in practice, but all these things, it's not productively efficient or effective. So in that anyhow, this is the paper I want to show that Hale's paper. You can see this many equations you have to solve to derive the baffle parameters. Whereas we have adopted a methodology, design of baffle, using the tool, whatever the design tool, taking the advantage of the design tool. Design tool, because design tool, when we do a real rate trace, what is happening? It will give, because real surfaces, real rate trace always gives the more realistic performance evaluation. So we use the design tools. So taking all the inputs from the design tools, solve iterative equation formulated in the reference one. You can see this reference. Anyhow, I will not go into the mathematical expressions. In this reference, if you do a iteratively solve using the real rate trace like coordinates, then the baffle parameters to block the direct ray will come out. And also the baffle will be a tubes. The tubes also, because all the tubes will be black painted, even then also black paints will have a finite reflections. So in order to curtail those reflections, we have to put vanes, like glass tops we call, or vanes it is called also. Those designs also can be carried out using the real rate trace of the design software tool. So this is anyhow, this also referred in the journal given in the reference to. So with that, we arrived at design. You can see these are the baffle parameters we arrived using those expression, which is integrated with the design and simulation tools. So these parameters are arrived. These parameters are not approximated to narrow field, wide field of view. These are exact parameters for the wide field of view. So you can see that this is again the baffle, whatever the tube baffle having the glass steps, also designed using the simulation and design tools. So finally, you can see that when we design a thing, it is always asked to be evaluated, because we cannot make a system then evaluate. It becomes a more costly and time consuming effort. So we have to do a numerical verification using the models. Here also the design and simulation tools comes in handy. Taking this kind of examples, a telescope was designed and baffle was designed. The solution of baffle parameter converts to, in 10 iterations, the baffle parameters, whatever showed earlier slides, it came out. Then with that baffle parameters, we can evaluate the performance of the system, like MTF. MTF can be evaluated because so many objects can be created using the design tools. This is the one of the objects, like a user-defined objects created, and that was implemented in the design. So we can evaluate the MTF performance. You can see this is the nominal MTF, and whereas when we try to reduce, control the stray light in a brute method or without any kind of proper design, we will end up this kind of reduction. However, this method helps us to come in between with both two methods with an optimum MTF up to the 0.5 normalized spatial frequency. Then you can see these are the baffles and elements constructed using the, here I will tell, I use the ZMAX optical design. Non-sequential methods are used for stray light models using the various non-sequential objects. So many objects are there which we can use it, make the whatever the objects, systems we want to make. Using that objects we can make using the non-sequential objects and user-defined apertures. We can make the entire baffle. Then that entire baffle is integrated into the system, because it allows, because in case of optical design, we always do ray trace. Rays are the virtual lines or imaginary lines normal to the constant phase surface of the light. So this is the always our optical design. It's using the ray traces only, not wave. Wave propagation is not used. Then 1 million rays are traced. There are collimated source, which also it's available in the tool. So we can flood the entire system with the collimated source, and detector element also can be constructed. These are the simulation tools which makes us more productive. And you can see that all baffles, first thing is we have to evaluate that whether this baffle is not allowing the direct rays. So we have to make all the elements absorber, mechanical elements, and mirror elements are all reflector, and lens elements are all 100% transmitter. With that, we have, you can see the analysis done over a plus or minus 20 degree, though the field of view of this system is 0.2 by 0.6 degree, even plus or minus 20 degree, you can see that there are no direct rays of stray light reaching the image plane. So this has been simulated and evaluated in the package before going into the experiment. Now we have to evaluate for the multiple reflections or reflections comes from within the baffle. If you don't have the vanes, these are the things which comes out. These are the secondary reflections which can reach the image plane. After introduction of the glass straps, you can see this, all these things subsides to zero. And this is also again that when stops are integrated into the system, again the simulation is done. So even with 40% reflectivity, no light reaches the image plane. So, and uniformity also, as I said, that uniformity also we have to maintain from center to across the image. So uniformity also maintained, that also evaluated using the design tool. With and without baffle, you can see that. Now going to this, up to this point, everything is we have made, so we understood, and everything is as per the requirement. Now this is the system. Building up the system requires three years kind of thing. Now the system is being evaluated and found the stray light magnitude is less than 0.6%. Our specification is 1%, but these are all mostly because of our fabrication tolerances and our testing limitations, because we may not be able to do the test how we are simulating. So those are the things made that stray light magnitude of less than 0.6%. So this overall, I could make that the design and tools which made us to helps us to conceive a system in small time duration with supported experiment also, which validated the thing. So coming to a refractive system, and refractive system more prone to this ghost. Normally in refractive systems, the ghost are all coming, ghost you may be seeing in movies also, there are multiple images are formed. So the ghost reflections can be evaluated, but in the case of what do you call so in this case, yeah, I got something. Okay, back ray trace we have to do, because we have to continuously we have to see various field it is working or not. So we have to continuously for that we have to do a back ray trace. Then the back ray trace helps us to do a continuous, over a wide field of angle of collimated lights, we can do it. But the design, these are all only thing I'll urge upon users. The simulation tools have all the facilities. How we will use it's one's understanding. Unless we able to understand the simulation tools, otherwise we will say that the tool has got a limitation. So good understanding of simulation and design tools helps us to carry out more efficient and effective way of our work. Let's see. It's not- Yeah, I have some slide is not moving. Just
You can reshare again.
yeah, I'm doing it. Yeah, you can see here. Oh, sorry.
Yes, it is moving now.
Yeah, you can see that this is the actual system without ghost. What I am showing is the ideal system. And the real system, there will be a ghost. Scene plus stray light. You can see this kind of images will form. So what is the contribution of stray light or ghost light can be evaluated. So here, what are the ways to control the ghost is one is that always we go for an anti-reflection coating on the surfaces that has been applied so that we are getting a 0.15% of seen light energy after this anti-reflection coating of 1% per surface average. Otherwise, what we have to do is again we have to do a redesign because we have to change the surfaces so that this ghost formation intensity will be reduced. So this is one of the simulation activity or understanding the system helps us to go for the fabrications. So finally, word of caution using the simulation tools. Simulation tools are efficient and obedient worker. Automation and intelligence are built into the simulation tools to carry out as defined or as directed to do. The simulation tool cannot do what is in our mind unless we give all the parameters like usefulness and utility of simulation tools in predicting the real world performance can happen only when user develop a good understanding of system under design and development, its influential parameters, modeling those simulation tools, modeling those whatever the systems in the simulation tools, and also more important is what parameters we have to evaluate. Otherwise, we will be evaluating a parameter which may not be a real world performance. So these are all important. So simulation tools usage also needs to be done with a caution. Let for an example, laser light source. Laser light source we use as a collimated beam or as a point source. When we have to use point source, when we have to use a collimated source, it is a question. Unless we understand, because the laser source act as a collimating source if it is lies between the beam waist and Rayleigh range. Within that, it acts as a collimated source. Beyond that, it acts as a point source. So unless we understand how the behavior of source, otherwise we will be making a mistake in the simulation. So this is the one precautions I'm just posing to users. Those simulation tools comes as an handy, but it should be used with a caution. So thanks. I think I hope I've made it. I hope that I'm
Yeah, sir. Thank you very much, sir, for very means I will say a crisp and very elaborate presentation covering all the aspects of design aspects which most of the participants may like to know. And you have rightly said that simulation tools are tools which needs to be used using the developer's mind. So we should understand clearly the physics behind it, what we should be defining, how we should be defining, and what results are coming, they are okay or not okay, whether we can cross verify it. So with this, thank you very much, sir, for joining us on this. I think we have done a first ever kind of a workshop on aerospace and defense focused workshop on electro-optics and photonic simulation. So thank you very much, sir, for joining us and sharing the very exhaustive, I will say, the experience of your design, how you have started your work and the entire design principles, as well as what one should be doing, what one should not be doing. And you have ended a very wonderful example of our laser, when it can be used as a point, when it should be used as a point source, and when it should be used as a collimated thing. With this, once again, on behalf of IEEE MTT AP Bangalore Chapter, as well as on behalf of IEEE Aerospace Electronic System Society, I would like to thank you for joining us and providing your wonderful perspectives. Sir, please stay with us. We are having one keynote speaker more and wonderful. We know we are late, But yes, if you can stay with us, it will be really nice. Thank you very much, sir.
Yeah, thank you so much. Thank you for your all kind words.
Thank you, sir. So I will now not allow Mahesh to take over because we are already late. So we will just invite Mr. Amit Agarwal, who is the area director of Ansys. So, and Amit, over to you. I think you will be covering your introduction in the presentation itself. Thank you.
Thank you, Puneet. Can you please confirm if you can hear me well and see my slides? Thank you.
Yes, you are loud and clear and slides are visible.
Okay, thanks again, Puneet. So a very good evening, all the respected speakers, dignitaries, and the delegates. My name is Amit Agarwal. I lead our Ansys team serving India, ASEAN, and ANZ region. And on behalf of Ansys, I would like to thank IEEE, MTT, and AESS for giving me this opportunity to speak at this forum. In line with the theme of the event, I'll start with the touching on the challenges bit and then going to the approach, some examples and few words about Ansys. We'll try my best to make up for time. So as you heard already from Director SAC about the challenges which we face on aerospace, if I look at space side, India is a prime example of cost reduction, more frequent launches, and commercialization. On the other hand, we heard about miniaturization of satellites, constellation, high pseudo satellites being driven through advanced telecommunication and observation, exploration, and weather forecasting. On the other hand, on the defense side, there is always a push on next generation systems and technologies, increase the lethality, survivability, stealth to stay ahead of competition. On the other hand, avoiding obsolescence is key for imported technologies. If I look at just the Indian aerospace and defense, one common thread is to catch up with global specs. When we look at global specs and come up with product design, they go ahead, so need to leapfrog. And more indigenization, we already heard in the opening talk, to reduce imports, increase exports, and not to lose the buzz on in the area of optics, quantum technologies. So all that resonating very well. With that, let me touch on the next topic about human vision. If you look at human vision, there are different five senses you could look at, and guess what contributes the highest amount to perception? It is indeed uh, yeah, human vision, which contributes to 85% of the perception, and that is key of all the audio, or I'll say touch senses, smell senses. Vision is the key, and hence we are here on this dedicated session. Let me quickly touch on challenges in optics. If you look at optical technologies, which are integral to many products, we heard enough about role of optics, the design of various devices, optics, and they enabling next generation technologies. Um, one key thing which is common thread is to help reduce time to market, not just reduce time to market, but also help come up with the optimized products for both performance and reliability. The other part is lit appearance. It is about how the illumination systems show up in the dark. That is key for some of the applications like signal sensors. And then it's about visibility, legibility, visibility be able to see, legibility be able to decode. Um, Regulations continue to drive to control a lot of optics applications, whether it is aerospace and defense or automotive. Again, perceived quality. It is about how light and the surfaces are interacting with each other, gives a very good perception about the quality of the object. It is key, and it's a key driving factor for across industries. Reflection issues. Reflection issues may pose a lot of challenges in terms of distract a pilot or a driver and have safety implications. Last but not the least, the lighting comfort. Lighting comfort has a role to play. When we talk about lighting comfort, we are talking about the not just the lighting design. We are talking about the level of light. We are talking about balance of contrast. We are talking about the color temperature, absence or presence of glare, and these things do make big difference. So there are multiple challenges, and what role simulation has to play. Let me quickly touch on that. Again, not go detail. It is established, proven that engineering simulation throughout the design phase, as you could see, and the manufacturing and operation stage has helped in lot of time savings, reduction in the overall cycle. So a reduction in physical prototypes, reduction in development time, overall equipment effectiveness, raw materials, and cost targets. Now, this audience of aerospace and defense are not new to this, and they have been at the leading front. So I'm not saying something new. We have partnered with aerospace and defense for over 2 decades, and they have been leading front. But just to make a point, simulation has a role to play. Now, moving very quickly to the simulation approach for optics design and simulation. So if you look at, on one hand, we start with image sensor, where we are talking about photonic component modeling. We're talking about chip level modeling, waveguides, sensors, microlenses. But then we also need to look at the optronic system integration, where we talk about lens stack optimization, optical mechanical tolerances. And then moving on, once we design the optical components, how they operate in a scenario where we talk about 3D environment integration, lighting, human vision perception. So we need to go all the way from a very small structural size to wavelength ratio to a very large structural size to wavelength ratio. And they are interdependencies. They are not mutually exclusive of each other. And that's where we need a holistic approach which can enable communication across all these 3 stages. Now, what are the building blocks? Very quickly touching on the design. So let's start with imaging sensors. When we design imaging sensors, we talk about optical efficiency all the way to signal to noise ratio and the optical electronic crosstalk. When we talk about lens design, we're talking about lens selection all the way to thermal effects on lens stack, the lens stack optimization to manufacturer design. And with respect to system housing, where we are bringing together the lens with the sensors and the structure, there is a lot of focus on system level integration, environmental effects on system, the thermal tolerance on system, the regulations. All these things have a role to play. And going further, again, coming back to the same theme, we are operating all the way from image sensor to a scenario. And that's where different models, different approaches are required. And that's where tool sets like numerical are apt with their algorithms for image sensor and CMAX for the lens design. And, and we look at the tool, which is right here, SPEOs for the design of scenarios. Now, let me move to some use cases. If you look at the use cases, the application range all the way from infrared search and track to high energy weapons, LiDARs, IR sensors, target signature, aero optics, and whatnot. So if you look at those, let's quickly come on camera sensor. So camera sensors, what are the different aspects of design of camera sensors? So we start first at the looking at the camera imager, where we can simulate all CMOS sensors to understand the quality of image produced. We can look at color depth, resolution, etc. by accounting for absorption, scattering, diffraction, other attributes, which are including the effects of micro lens structures. So this is about the camera imager. Then we can also study the optical properties of lens and simulate various lenses, related aberrations, errors, and perform thermo-optical linked analysis to understand the optical variations caused by anomalies caused due to thermal effects on structures. So we are talking about photonics, we are talking about thermal effects and on the structures. So it is getting more and more complex. And then we move on to simulating the entire camera in its environment to analyze light propagation through ray tracing. We can define properties of the camera and the source of light, various objects in the field to understand the desired outcome, whether we'll get that outcome with the camera or not. And this is based on optical physics to deliver accurate results. And this can be performed across the visible spectrum, near infrared, as well as far infrared range of light, both. With these capabilities, we can define all properties of a camera and understand its performance boundaries, and so that you can decide if the system meets your objectives. So if the desired objectives are not met, you could do sensitivity parametric analysis to help you achieve that fine balance which is required between cost, performance, and anything else that matters. So what are the benefits which people have achieved? Reduce iterations from 100 to 10 cycles between subcomponent system integration, expand design testing thanks to virtual prototyping with simulation, reduced physical measurement campaign, and that has a long way to go in accelerating the whole product development cycle. Moving to an example, this is a very quick example. Majority of people would be familiar with this James Webb Space Telescope. It's a proud moment to say that we were closely associated in the design and development of this telescope. The goal here was it consists of 18 hexagonal segments, and this primary mirror was required to function as a single mirror with a surface smoother than 100 nanometers. How did they achieve? The engineers designing this telescope, they use ZMAX software to simulate the complex optics of the numerous gold-plated mirror segments, designed and test every step of the alignment from segment search to the final phasing, and that has made a difference. As you can see in the picture, let me just turn on the pointer. There is a comparison show of a Hubble primary mirror with the JWST primary mirror, how they are different and how challenging it would be to design this. But it's a proud moment for us. Moving on to a very simplistic, a relatively simple example from defense perspective, rifle scope design. If you look at rifle scope design, we are talking about basically clubbing two designs, objective and the relay and the relay and the eyepiece. And they will be design constraints such as cost, size, getting imaging quality, getting focal length close to infinity. And that's where simulation has a role to play to address, overcome these constraints, help get most optimal design. This can be achieved. You can look at parameters like MTF, we just heard, spot diagram, ray aberration, etc. Moving on is the next example on low Earth CubeSat application. And this audience would be very familiar with it, but let me just still share. CubeSats are a class of micro and nano satellites, which are very small, weighing less than 10 kgs. And these satellites are built for dedicated purpose, such as Earth observation and communications. And smaller size and weight is a big advantage. They could be easily sent on missions, but the technical challenge is to fit the electro-optical systems within such dimensions to be able to operate in a very hazardous environment for a long duration time. That is a challenge. We have these satellites as full-fledged computers in tiny proportion, and they need to operate in adverse weather, temperature, and vibrations. So what is the role simulation has to play? We can help simulate with physics-based accuracy, helping you design, develop complex systems first time right. And we have customers designing even laser excited systems for CubeSats. So there are more details to this example, and anybody is interested, please reach out. We can share more. I'm just trying to go through very quickly. Moving to predictive target detection. Coming to defense application, I think the key part is to look at let me just try to make this small. Yeah. So, so the key important areas to detect and identify airborne objects which are flying into guarded airspace, and it becomes harder and harder to detect the presence of enemy due to anti-detection technologies which are built into aircrafts. And sometimes these aircrafts could fly as high as 50,000 feet above the ground. Detection through visible range can be very challenging in these environments. How do we get around that? We use thermal cameras, which can help detect objects based on heat signature. And this heat signature could come from engine plume and with the mix of exhaust gases, which can absorb light frequencies different from the characteristics. And these characteristics can be detected, analyzed through long range infrared sensors, and the target signature can be detected. However, the environment factors can impact the detection. For example, presence of thick layers of cloud. And this is where simulation can help perform optical coupled multiphysics analysis to perform the DOE, understand the parameters of operational efficiency. What does it do for you? It helps you to achieve predictive target signature virtually, expanded test environment, and reduce physical measurement campaign for such scenarios. Moving on, the next very interesting case study is we already heard from earlier speaker, Dr. Senthil Kumar. Let's talk about just the workflow for electro-optics infrared simulation from component all the way to the mission simulation. So on the left side, you would see component modeling going on the extreme right to the mission level modeling, and the products being mentioned at the bottom. So starting with, we can design the complete lens systems and perform optimization, as we just heard earlier. Then this camera system can be imported to perform stray light analysis and optomechanical analysis and tolerancing studies at the package level or at the components integration level. We can also perform sensor integration, packaging study, aero-optics analysis, and perform structural, thermal, optical performance analysis, also called as STOP. We can then build a ROM to be integrated into digital mission engineering, which is right out here. So we are taking the fidelity of optical, thermal, mechanical calculation through a reduced order model, taking it all the way to the mission on the right. And the high fidelity simulation is integrated into this so that you could have a ground, space, air monitoring. And to visualize the dynamic performance of these systems, it's not limited to geographical coverage, but also performance and detection characteristics over time with 3D visualization. So this is the power of bringing component modeling all the way to system and mission level. Having said that, very quickly touching on what are the critical capabilities needed. What are the critical capabilities needed to do this analysis? I think if we look at the pyramid of design and development, at the bottom you can see components. Component subsystems, they are modeled today with highly accurate physics simulation. But at the next level, when we talk about systems of systems and systems, they need very fast models to be operated. Usually these are plant-based models. But how do we get the best of the both worlds? By using reduced order models from components which bring the fidelity of highly accurate physics, but in a very rapid plant models through reduced order models. And then they can interact with missions. So you are bringing the physics and the accuracy of the high fidelity physics from components all the way to the missions. And that is kind of need of the hour if we really want to bring high correlations. Moving on, the other capability in terms of tool sets would be accurate and validated and proven. In aerospace and defense, it is non-negotiable. It's very clear that it should capture physics and the accuracy. At the same time, we should also realize that one tool cannot solve the problems. They would be mix of tools in-house, third parties, and so on. So there will always be a heterogeneous multi-tool workflows, and deployed simulation must operate in an open and interoperable manner. And last but not least, the workforce enablement is as important as providing latest tools and technologies. And that is where our focus has been, with 50 years of history, to focus on most accurate physics-based simulation. We have always believed to be open and collaborative simulation environment, like a Android of simulation, if you may call. And there is tons of investments made in bringing up center of expertise, which offer online training, technical support, consulting, professional services. For us, enablement is as important as providing latest and greatest technologies. So with that, I'll just try to take one or two more minutes. Just wanted to highlight simulation has been our bread and butter for 50 years. That is what we do. And for us, the satisfaction of our customers is foremost, and this is an important metric we highlight. And one more thing is we have stayed focused, open architecture, and that really has helped. We don't want to limit ourselves to a particular workflow, so that we can customize with your workflows, your approaches. This is how Ansys has grown. But just to focus on this journey has brought the latest. We started with the SPOs, which came through Optis, then Lumerical, which brought photonics capability, latest edition of ZMAX. So this continued focus on physics-based simulation has helped us to bring this capability today we have. Now, just very quickly, you could see our foundation remains physics-based simulation, from structural fluids to electronics, optics, photonics. Why is this important? Because if we look at any of the devices we just heard, it is not just about photonics. It's all about electronics, mechanical, optics, everything working together seamlessly, so that the component of the system we design can operate in hazardous environment in a very reliable manner. And then on top of it are systems, embedded software, safety analysis, cyber security. We heard about data security earlier in the opening presentation. Digital mission engineering, cloud optimization, multiphysics, and so on. So with that, let me summarize. We see a tremendous growth potential. We just heard in the opening talk about quantum physics. We heard about role of optics, and we are excited to be here. We feel simulation has a key role to play, and what is needed is a very holistic approach for photonics, optical systems, and missions. And accuracy and validation cannot be compromised. At the same time, it is important to have an open collaborative platform and focus on people enablement. With that, thank you for listening.
Thank you very much, Amit, for your wonderful presentation and emphasizing the importance of simulation and how Ansys various tools can play a very meaningful role in reducing the overall design, means from concept to what you can say rollout. That entire time cycle can be reduced with the help of simulation tools, and they are very important because sometimes it may so happen that we will not have any option to have, like in space we will start with engineering model, then prototype model, then qualification model, and then flight model. So it takes a longer lead time. So we will have most of the time that okay, you do simulation and directly go to the proto flight and then flight model. So that kind of scenario when and the time given to designer is very short, these simulation tools definitely play a very important role in any engineer's life. And of course, Ansys is playing, and I'm very happy to see that you are having now solution for all the important things. And when we talk about digital mission engineering, truly you are having solution, and each vertical is being what you can say. Some solution is there for each vertical. So with this, I would like to thank on behalf of IEEE MTT AP Bangalore Chapter as well as IEEE Aerospace Electronic Systems Society. Thank you very much for joining us and sponsoring this event. First of all, that I think this is the first time we are having this kind of a collaboration where we are having all the stakeholders in a single platform. Means we are having the users, we are having the software tool providers, and then we are also having designers and then participants. With this, thank you very much once again. And if you are having anybody is having any questions, please type here, and we can take up one question only. Okay, so there are so many appreciations for you. Real questions as and when comes, I will pass on to you. Sure. And then we can take up. Yeah. Okay. Thank you.
Thank you, Puneet.
So we are almost 1 hour delayed, I know, but yes, we will try to move on towards the last leg of this session, which is a round table. And this round table, I will just try to share my screen. Just let me know my screen is visible.
Yes, sir, visible.
Very good. Yeah. So this roundtable is on evolution of electro-optics and photonic systems in aerospace and defense, challenges and opportunities. And along with me, we are having a very eminent experts who are joining me, starting from Dr. Meena Desan. She is from LRDE DRDO. Again, we are having Dr. Ranbir Mandal, who is also scientist as well as head of optical design division IRD DRDO, one of the very prominent lab working in this domain. Then of course we are having Shri Amitvikram Kurulkar sir from ISRO, and to give what academia is doing in this field, we are having Professor Shashank Kumar Selvaraja from ISC. He is also chairing this National Nano Fabrication Center And yes, because we are talking about simulation, so from simulation software side, we are having Raghavendra Bhatt, who is head system and optics business unit area, India. So I have made slides for a very elaborate introduction, but I will be giving a very crisp introduction of all the panel members, and then we will be directly going to our panel discussion. So Dr. Meena Desan, she graduated from NIT Calicut as well as PhD from ISC Bangalore. She is also having MBA degree, and she has worked doing various DRDO lab. But the most important thing is currently she is working as a senior scientist at LRDE and is leading photonics related development activities at LRDE. So welcome, madam. Thank you very much for joining us. Our next speaker is Dr. Ranveer Mandal. So he has completed his BSc Physics from Ramakrishna Mission Residential College, BTech in Applied Optics and Optoelectronics from Department of Applied Physics, Calcutta University. Now it is Kolkata, and PhD from Calcutta University again. As far as relation and working with optics is concerned, from 2003 to till date, he is a scientist at IRDE, DRDO Dehradun, and he has executed several projects which includes design of optics for day vision, image intensifier tube based, laser based optical system, and then design of optics for MWIR and LWIR thermal imager for different DRDO projects. Our next speaker is Shri Amitvikram Kurulkar. He has done his MSc in physics from IIT Mumbai and MTech in applied optics from IIT Delhi. Presently, he is division head of Hyperspectral Optics Division, HOD, in Optical Systems Group of Sensor Development Area in Space Application Center. This division is responsible for the design and development of optical sensor for hyperspectral electro-optical payload for various Earth and planetary mission, and he is also associate project director of one of the very important mission of ISRO, GISAT-2, which is the geoimaging satellite. Then we are having Professor Shankar Kumar Selvaraj. He is a Ramakrishna Rao Chair Associate Professor at Center for Nanoscience and Engineering. He is also the chair of National Nanofabrication Center, a very important facility contributing to the national development. And he has spent over 15 years in silicon and integrated photonics, photonic developing state-of-the-art CMOS process and device technology for high-speed optical interconnect and sensing applications. And then we are having Mr. Raghavendra Bhatt, who is the technical head for systems and optical business units. He mainly works with customers to provide technical solutions in the area of safety and mission critical software development, electro-optics and photonics, functional safety analysis and system simulation tools. With this, I know I have cut short the bio, but because we all want to listen them rather than listening their bios. So we will be hearing their perspective right now, and we will be doing a round robin. So I will be starting from one speaker and at the end, and then again we will be reversing back from the end to first one. So like that we will be doing. I hope it is okay. I would like to invite all the panelists to switch on their video and their mic as well, so that at least I will know that we can talk. Dr. Mandal, I can see you. Can you just unmute yourself and speak so that I can see that audio is working?
Am I audible?
Yes, you are audible. Yes. Meena madam, can you just unmute yourself?
Yes, I have already unmuted. Very good evening to all.
Very good evening, madam. Amitvikram sir, can you switch on your video and audio as well? I can see Mr. Bhatt video. Yeah, good evening. And Professor Sarvilash? There?
Yeah, I'm here. Can you hear me?
Yes, I can hear you.
Yeah.
Please switch on your video if possible,
I think I'll do
so
it.
that audience can see that.
I'll do that.
Thank you. So now I can see you as well as hear you. Yeah, so I have given a very small introduction about each one of you, but I will give you an opportunity to talk about your work, what you are doing and where you are doing, what technologies presently we are working and how you are seeing the future trends there. So the first question, which is open for all the panelists, is what are the new and emerging technologies in the world of optics and photonics, and on which area you are currently working? So I will start with female first. So Dr. Meena, over to you.
Yeah. Well, very good evening to all. And first of all, I would like to thank the organizers to give me an opportunity to be part of this event, to share my thoughts on this particular area. So I'm basically from the radar background, so that you have come across through my introduction. So in the recent years, if you see, from a greedy perspective, we can tell that if one radar or one sensor can detect, which is capable of operating in multi-band, and if we are able to detect the target, then track the target, confirm it, and moreover, if we are able to give the image perception of the target along with the environmental mapping, that will be the best solution. But we are little too far from this solution, but I can tell you the recent advancements in the technology, especially the photonics and the quantum, have led to a scenario where we can address some of these issues. For example, if you ask me, the I will only talk about the even though in defense there are a lot of applications, I will stick to my discussion only to the radar applications. So if you ask me this question, I will answer two areas. Are one is photonic sensor and the quantum sensors. That is photonic radar and the quantum radar, where we are dwelling upon, especially in the case of photonics radar, we are going ahead with microphotonics. That is more, it is an interdisciplinary topic between the RF and the photonics, and we are trying to incorporate many of the RF functionalities which is superior in nature in a comparison with its RF electronic counterparts. I'll just take, I don't know, Dr. Puneet, can I know for each question how many minutes, so that we can manage the time also very well? Can you let me know? Hello.
Yeah, you are having another 1 minute, madam. You can go ahead.
Okay. So I just wanted to tell you, in the present scenario, this photonics gives us a solution where we can have wide bandwidth. That is, by using the same architecture, we can have the radar sensors from the RF to millimeter wave. And similarly, so many things, especially I will just summarize, we can have the RF signal generation and some of the signal processing functionalities, and also the distribution. At present we can do it by using the photonic components. And coming to the quantum radar, already the first session, during the first session, he was mentioning about the quantum communication, but I just want to throw one highlight on this. With the quantum sensors, we will be able to detect target even in the presence of the noise also. Maybe when it comes back to my session again, I'll more dwell upon it. Thank you.
Thank you, Dr. Meena, for setting the, I can say, stage with providing a lot of information, and just putting your perspective as if for all the problems there is a solution with photonics and quantum technology. So thank you very much for providing that perspective. Now, we have heard several information and perspective from the industry side. I think I will give chance from academia this time. And Professor Selvaraj, over to you. The first question, what are the new and emerging technologies in the world of optics and photonics, and in which area you are currently working? So over to you, Professor Selvaraj.
Hello, Dr. Puneet. Amit Kurulkar here. Am I audible to you?
Yes, you are audible,
okay,
sir.
Okay, fine, because I was not. Okay, fine.
Yeah, so you can switch on your video, sir, so that everybody knows.
No,
that,
I don't have a video, but
okay,
I'll be.
No problem, no problem.
Yes.
Okay. So, first of all, thanks for organizing this panel discussion around electro-optics and photonics in particular. It's relatively a broad topic. However, we need to have some focus and then discuss around the requirement that was put forth by the keynote speakers. So, if I have to talk about what I do and what our research programs are, primarily my research group works in the area of photonic integrated circuits. So our primary goal, or let's say, focus here is to make circuits that can use photons and realize optical functionalities that you have in bulk on a chip, right? So including dispersive elements, splitting, combining, WDM. So all those functionalities that you have in bulk, we would like to realize it on a chip. So why do you want to do this? So the bulk optical functionalities are good in some case. However, if you want to miniaturize and reduce the noise and have a better control over the optical process, you need to have these kind of miniaturization. And it's not just reducing the size of the system, but also the performance as well. So that is where photonic integrated circuits come. So what do you do with it, right? The next question is, okay, I miniaturize, and what do you do with it? You can do literally, anything and everything that you do in the bulk domain. So including transportation of signals. When you talk about electro-optic, you're talking about electrons to photon conversion and then photon to electron conversion, and manipulating the photon for its polarization, intensity, phase. All these manipulations could be done on chip, right? And if you can do that, so what is the advantage? What is the application space that you can target? You can look at data transmission, short reach, long reach, and you can look at radar application that just what Meena was talking about, and then imaging applications. Right, this need not be very specific to a system, but you can still do imaging out of it. You can do sensing, for example. So you can do sensing where you can create very strong light matter interaction. So that is very crucial in doing optical sensing. So your circuits helps you to do that, because unlike in free space, you have a millimeter or scale beams that are interacting with the object. However, in this case, in a circuit, you can actually reduce this interaction volume to sub micrometers, right? So a micrometer's cube is the volume interaction. So you become very strong localized interaction that you could do. So this is sensing is another thing. And then the other thing that was also flashed in one of the slides from the SAC director is quantum photonic circuits. So photonic circuits are there, but if you want to scale up, optical systems are not going to help, right, in building large quantum systems. So quantum photonic circuits are the only way to move forward. So these are all the domains or platforms that photonic integrated circuits could help, and that is where we are actually trying to contribute. And when I say photonic integrated circuit, I mean, it's not just the processing, but also integration of light sources and detectors as well, right? So you have a fully integrated circuit, meaning you can generate photon on chip, you should be able to manipulate the photons, and also you can detect the photons. So that's the ultimate goal in such photonic circuits. So that's briefly the area that we work on.
Thank you, Professor Selvaraj, for nicely summing up your area of expertise and work on the photonic integrated circuit. Now, I will quickly move to Dr. Mandal, who is from IRDE, one of the most important labs in DRDO working in this technology. So, Dr. Mandal, again, over to you. Please let us know in which area you are working, and then what are the recent technological trends and emerging technologies in the optics and photonics.
Okay. First of all, thank you for giving me opportunity to share my view in this panel. As you understand, this
we are not able to hear you, Dr. Mandal. I think you can come closer to your mic. No, again, I am not able to hear you. Initially, it was okay. Yeah, very feeble voice is coming. Very feeble. You have to remove your now you are using that microphone, so you have to remove your microphone from the PC, then only we can hear you.
Arko?
Yes, now it is working. Yeah, please go ahead.
Okay. So actually, this IRD is responsible for providing optical instrumentation for different DRDO projects. So from the charter of IRDs, this thing, first thing is that we are giving optical solution. Second is we, side by side we are doing research in optics, photonics also. Now, for my division, our goal is to provide the optical design solution for this optical system. Okay, so basically my domain is just design the front-end optics. Now our design actually deals from visible to up to long wave infrared band. We cover all the optical spectrum, and the recent trend is that combining different band to a common channel. Say 10 years back, we have to design separate channel. For visible, there will be a separate payload. For sweep band, there will be separate payload. For LWR band, for MWR band, all are separate. So it gives a bulky system. Solution will be a bulky system. Now the trend is to combine all this channel so that our system should be compact. It should have better throughput as well as weight and power requirement will come down. First thing is this. Apart from this, now it is not only the optics. Actually, the solution, the bulk optics or the front-end optics purpose is to collect the incoming radiation in visible spectrum that to be focused on a detector, so which will transfer that optical signal to electronic domain. Then there will be processing, and ultimately it will be displayed again on a display devices. So initially we have to have our work up to that signal, converting that photon to electron, that part. But nowadays we are making system where we can combine that signal processing. Say we are introducing some known aberration to the system, and we are correcting this error through image processing. So it will reduce the load on the optical side, but through processing we can improve the overall performance.
Thank you, Dr. Mandal. Thank you very much. Now I have to stop you and we will go to our next speaker. Now we have heard from academia and from industries. So I will like to go from simulation point of view. Mr. Bhatt, over to you. According to you,
Thank you. Good evening, everyone. And first of all, thank you to be part of this panel. So most of what I wanted to talk has already been brought out very clearly by my co-panelists. So I would like to bring my perspective as a simulation solution provider. So being a simulation solution provider, I must say, we are fortunate to have the opportunity to work across multiple domains and interact with customers about a wide variety of applications. So we work with the aero, we work with defense, space, automotive, medical, and other industrial customers as well who are working on cutting edge technologies. And some of the topics we come across frequently are the integrated optoelectronics, which is brought out by my co-panelist already here. And this is a very important research area. So there is a very high level of research and development focus on the subject. And this also extends further into LEDs and OLED-based display panels, solar cells, laser diodes, optical waveguides, modulators, etc., which are all the current topic of interest. And another trending topic is freeform optical surfaces. And there are lots of possibilities with freeform optical surfaces that are yet to see their full potential. So simulation can play a crucial role in the advancement of future potentials in this area. And one more topic that was already brought out in the discussion is about miniaturization. And this includes compact, lightweight, and low power optical systems in many areas of applications. This is a generic trend that we see across the domains such as micro and nano satellites, like Amit has spoken about earlier, all the way into the capsule robots in medical applications. And of course, the communication, navigation applications in aerospace, including the technologies, as the Director of SAC has spoken about earlier, are definitely the focus of continuous research. Now, high-end thermal cameras, night vision systems, monoculars, binoculars, telescope, microscope, these are all very generic applications that are continuously in the high level of focus, topic of interest all the time. And again, like Amit has talked about, CubeSat is a new technology trend these days, especially in space. And these are small satellites about, let's say, 10 centimeter cube with a weight in the range of between 1 to 2 kgs built for specific purposes. Again, that's another important, interesting area for optical systems. Head-up displays in aero and automotive are getting to the next level with augmented head-up displays with synthetic image being displayed on the HUD. And there are a lot of work going on this topic as well. And of course, the general lighting topic is another interesting area which are continuously pushing the boundaries of what's possible with lighting. And the last topic on the medical side, devices such as ophthalmoscope, endoscope, and capsule robots that I talked about before are once again have a lot of optical technology trends and the future potential. And it's very interesting for us to get engaged with our customers, help them address some of their critical challenges they're facing in the design and development of their optical as well as electro-optical systems. Thanks.
Thank you, Mr. Bhatt, for nicely summing up the whole gamut of electro-optics and photonic system and how simulations are playing a very, very important role and how Ansys is providing solutions to them. Now coming last but not the least to Dr. Amitvikram. Sir, we want to know what are the new and emerging technologies in which area you are currently working. Over to you.
Okay, thank you. Thank you, sir, for inviting me for a very good discussion we had till now. Actually, we are working on hyperspectral imaging spectrometers for spaceborne and airborne spectrometers as well as for planetary missions. We have worked till now on the visible and very near infrared to the SWIR regions. We have realized spectrometers for the GISAT payloads, the airborne payloads, and the latest ones was the Chandrayaan missions. These were from typically in the visible range, it was from 400 nanometers to 2500 nanometers. And for the Chandrayaan, it was from 800 nanometers to 5 microns. Typical spectral resolutions were around 4 nanometers, and number of bands varied from 150 to 256. And currently, these typical spectrometers are very modular level, very compact, using a convex grating technology, like an Offner based spectrometer. So it can be modularly evaluated, as well as we do with the in-house fabrication also for the gratings and the mirrors we have started. Currently, we are working on hyperspectral imagers in the long wave infrared region, that is from 7 microns to 12 microns, using the Dyson type of techniques, Dyson lens and concave gratings. We are designing using simulation techniques for this, the stray light analysis and whatever our previous speaker, Dr. Senthil, talked about. Currently, we are working on that. Similarly, we are, as my co-host and the panelists mentioned, the current technologies in the hyperspectral imagers, we are working on free-form optics to make it more compact, make it more aberration-free, and having a good resolutions as well as spatial resolutions for a good imaging quality. Now, these are the current challenges. What are we facing are, as we go to the long wave infrared imagers, we have to thermally design these spectrometers. They have to be, the optics needs to be cooled to achieve the required NEDT. The background needs to be limited. It should be also a compact payload. So these are the technologies we are currently working on. And
thank you very much, sir. So yes. I will just stop you here because now I will ask another question which you are trying to explain, and because I will be starting from you only. Okay, and you have nicely summed up the various areas of sensor development and what are the problems involved there. So I would like to know what aspect of sensor development or validation task takes the most of the effort, and what are the key challenges.
Sir,
over to you.
Okay. The key challenges and the tasking is we need to design and fabricate the components for use of this in this payloads. Now the key challenges is to how good is the component tested. It will be how the component will be fabricated. That is the key challenge. So suppose my convex grating, I can measure with a test bench the grating efficiency correctly, the spectral resolution correctly, and the grooves per mm, whatever is, there are no distortions, there are no secondary higher orders due to the imaging. Then I'll be able to fabricate it also correctly. So it is an iterative process, both metrology as well as fabrication. So the testing of an optical system, both at component level as well as at the system level, be it on a hyperspectral imaging payload or a large optical system like a telescope, the testing of that at ground and then space simulation using a thermovac chamber, then its effect for gravity, effect for vacuum, the lenses have the refractive index change, what will be the offsets for vacuum, then what various stresses due to misalignments, the distortions due to mounting errors, and the light weighting patterns, what are the distortions calculated, how are they measured, what will be the setups like for these measurements. The interferometrically we try to measure this. So these are the real challenges for our development. The key for component design to realization, the testing of that, as well as the system design and the system testing for its space use. And to use that while testing on ground. These are the key challenges, whatever you face.
Thank you very much. Now again I will come to Mr. Bhatt. So Mr. Bhatt, you have heard the pain points. Now, how using your simulation software one can solve these pain points?
Yes, definitely. And just to add on top of it, we see that these days sensor development itself is becoming increasingly complicated. And our customers are developing optical systems, which in fact are pushing the boundaries in terms of optical performance, let's say, such as higher resolution or higher sensitivity, improved color perception, reduced noise, better low light performance, and so on. The challenge starts right at the sensor image, the imager design itself. So typically, we would use CCDs or CMOS sensors. Each have their own advantage as well as disadvantages. So we have efficiency, sensitivity, color perception, blooming, crosstalk. You said a lot of such issues that play an important role in the selection of sensor itself. Now, on the other hand, the lens system is as much important as the sensor itself. The design and development of high-quality optical lens system takes significant efforts. There are multiple optical aberrations, such as spherical aberration, chroma aberrations, astigmatism, barrel distortion, pincushion, wavefront errors, and many more. And there are issues of stray light within the lens assembly, like Dr. Senthil was talking about before. And then there are issues with the thermal and structural interactions that could contribute to the optical errors, which could be especially important for high-power laser devices. And like the way how I just heard about a couple of pain points, so these simulations or these systems need to be designed on the ground, and later they would be going into space, or their operational environment is going to be very different. They will suffer through a lot of adverse effects. For example, it could be noise, or it could be vibration, or it could be various temperature differences. So these things need to be tested on ground, and they must also be tested in an environment where they eventually are going to be operating. So these things are not really easy for us to replicate on ground. So simulation is the only way where these parameters can be effectively tried, tested, visualized, and we could see where things are going wrong. And then we can fix the issues and then later put them into the actual deployment. So Ansys simulation solutions like Lumerical, ZMax, as well as PIOS help our customers perform simulations from all the way from the nanoscale to the system level to ensure the most challenging issues are identified and addressed before going to the prototype. So this is the most important benefit of performing simulation before we go into the prototype.
Thank you, Mr. Bhatt. Thank you very much for giving a very crisp answer about how you are taking or solving the pain points of the users. Now I will come to Dr. Mandal. Dr. Mandal, you have heard Mr. Bhatt. He told there is for any problem, there is a solution with the simulation. I would like to know your perspective, your experience in using simulation tools, and how you are able to validate and use it in your sensor development. Also, which are the critical areas where you still feel that there can be improvement in the simulation softwares?
Okay. So the answer will be, it has many dimensions. As I am a designer, optical designer, so if I start my career in 1998, okay, and that time we don't have any good software in India. So we have imported Code 5, GMAX that time. Okay, and we started designing this thing, and we have our optics background. So before starting a design software, we have to have a sound knowledge about optical system. Okay, that is a condition that time. Now after that, you see GMAX come up, their market, they come up very, what I say, rather than Code 5, they come in a very big way. Okay, and as on date, what is happening? People are using GMAX just like a video game, and they are getting some solution which is not realizable. By chance that may be a good design. But what I find that lot of people are design, and I can say it is actually sometimes I can say bogus design, because they are not able to use the software, proper software. So my first problem is manpower. In India, you see there are only 2-3 places where optics are taught. So it is a problem in India. Second thing is that, okay, you see, in 2000, we have only spherical surface generation facility. After that, we graduate to aspheric surface facility. Then we matured to use of diffractive surface. And as on date, we are moving from this to freeform surface. Okay. Simultaneously, to design, to fabricate it, to characterize it, it has its own complication for each and every technology. Okay. Now, as on date, this use of freeform optics in optical imaging system, it is, I will not say it is as on date very mature. Gradually, it is improving. Next is that, say I have designed an optical system. Now this optical system will be inside a mechanical housing. So a very good optical system, when it goes to a mechanical housing, this stray light, all these things will be in picture, because through simulation, through optical design simulation, you are ensuring a very good image quality. But while you are developing a prototype, we are finding so many problems, unwanted.
Yes. Dr. Mandal, you have very, very pertinent questions. I think.
Okay. Then
our friend.
Next is that, say we have designed a very good system, but your environmental environmental factor, that will also degrade your performance. Okay.
Yeah. Thank you, sir. I will stop you at this point because I have to go to another panelist also, and you have raised several questions actually. And one of the questions were that there are simulation tools are not accurate because they are taking ideal conditions. So I will come to Professor Selvaraj. So your domain is such that, in fact, in India, we don't have fabrication facilities also. And your entire design has to be based on the simulation. And I don't think most of the simulated design you will be able to fabricate and test it and validate the simulation. So all the more it is important for you how you are utilizing these simulation tools accurately, that whatever design you are doing, they when suppose in case you are able to fabricate and realize it, they are accurate. And second question, again in line with Dr. Mandal's question, that there is a very few human resources available because very few universities are teaching these days optics and electro-optics domain. So how ISC is taking care of that? So these two questions, over to you.
Right, thank you. So I just want to just clarify your first statement that the domain that we work is reasonably advanced. Thank you for acknowledging that. But I want to just clarify that we have fabrication facility to make photonic circuits here. So my group is an experimental group, and in the past 8 years or so, I just had only 2 theory papers. So we are.
I'm not talking about ISC. ISC per se, you are having.
I'll come back to that. I'll come back to your question. So the facility is here. We can make photonic circuits and photonic structures of reasonable resolution. We're talking about sub-resolution, and sub-wavelength structures could be fabricated. So that is taken care. And we have nano centers coming across the country. And right now, there are centers, reasonably, well-equipped centers across IITs. And now we have a program that opens up this facility to anyone in the country, any academicians, any industry, right? So they should exploit this opportunity. And they are being done so, right? Our facility is open to anyone in the country. The important question there is how do we use simulation tools? So in our lab, we have a couple of different type of tools, right? Starting from a FEM tool to FDTD and simple FD and so on. So there are different platforms that use for different purpose. And there is a big difference between optical design and the circuit design. So optical design, ray tracing is still okay.
Yes.
But we cannot do that. So our scale is so low that you are talking about the scale of these structures are the wavelength scale and sub-wavelength scale, right? So ray tracing is not going to work. So we primarily work with EM tools, and that is very, very expensive in terms of computational resource requirement the moment we start making the structures reasonably large. So these are all going to be, let's say, even a 10 by 10 micron is a large simulation space. You want to do a thorough analysis of the structure, right? So computationally, it's very heavy, and you cannot run these on a simple laptops, right? So you can do certain things with your laptop, but it's not going to work. You need a specialized missions to do this, right? So there is a big difference between optical design and circuit design. And the next thing is about what is the challenge that you have in designing this, right? When you make these devices, intrinsically you have tolerances that come into picture. So you can have anywhere between, if it is a very good process, anywhere between few percentage, let's say 2% to 1% to about 5% variation in the space. So in principle, you should be able to make this tolerant analysis in the design. However, we are talking about very small fine features, right? I'm talking about 500 nanometer, 100 nanometer features. And there, when you're fabricating it, you will have surface undulations, right? Roughnesses that are the order of atomic scale. So this becomes even more challenging because your light that is propagating or interacting with the structure is going to scatter and react to these small variations, right? So in simulation, it is reasonably hard to incorporate all of this because, again, you need a high resolution in the simulation space, and your computational resources are again going to exponentially increase. So there is a price to pay if you want to go towards simulations that are very close to the final device. So that's where we need to have better platforms in approximating these the real life scenarios, right? So that is where the challenge is. And if you ask me, I would do a simple calculation to have an idea how this particular configuration that we have come out with is going to interact with light, and then we will just go to this fabrication part, and then take the limits from there, and then feed it to the simulation. So I'm not going to do a full-blown simulation before going into fabrication, because that's a never-ending loop, and you need to have inputs from fabrication. So that is the main part of your question. And the second thing is about the manpower, the trained manpower. So trained manpower in the let's say there are two parts. Again, the traditional optical design, and then you have the upcoming advanced photonics design and so on. So in both, we have very limited programs in the country. It used to be very good, but now the program is restructured, and you have some places that are good in optical design and some are with fiber optics. There is no good program, let's say, photonic program in the country. So that's a challenge, because the problem that we see is it is easy to launch an MTech program, right? We do have PhD programs, right? That's for research. But if you want trained engineers to work in research labs and in industry, you are looking at primarily BTech with some exposure and MTech specialized people, right? So if I'm going to create an MTech program, right, I need to have a path for these students who are coming in, whether there is enough employment in this particular domain, right? So the MTech program attracts more people that has a good visibility in having industry positions. And right now we don't have a very vibrant optical design industry or fabrication part, right? These are all very small specialized groups where the number of students or staff that you need are very minimal. So having a large program across the country is also a challenge. So this is again a chicken and egg problem, right? So we need to find a way to sort this out. But going forward,
Thank you, Professor Sarvraj. Thank you very much. So we could understand your perspective that yes, there is a crunch of human resource, but even though you want to start a program, students will join only if they see that there is a future prospect is there and job opportunities are there. Now coming to Dr. Meena, I would like to know, you are responsible for photonics activities in LRDE. So what are the key challenges you are facing mostly in your photonics development, and what are the validation tasks you are taking with the help of simulation, and how they are helping to you? And I would also like to hear from you, do you also feel that there are really a crunch of experts in photonics field when you are because you are leading the group, so you will be finding out who are the key people who can help you. So what is your experience in that area as well?
Okay, well, thank you. And when we are working in a newly evolving field and we are trying to incorporate something totally new, obviously there is we depend upon, first of all, we will be depending on the simulation or the modeling tool before prototyping. And for example, if we take from the perspective of a radar realization, I already mentioned that we can for example, if I want to generate a transmit waveform in a radar itself, there are n number of ways in the photonics itself, in microphotonics. So which one is best for our application? So the first level we have to evaluate which is best. So we will surely depend on simulation tool. But the thing is, how far the simulation, it's only, according to my perspective, all simulation tools are only an aid for approaching to a realistic situation. So how far we are able to model a system with, okay, from a system perspective, I should tell that first we may be doing at the component by using various components, the system modeling. Then what happens is, if you are able to model a system with, for example, the radar transmits signal generation, I told you in various fields we can apply the photonic methods for the RF signal generation or the detection of the echo signal or the optical beamformer. All these domains, if we want to do the analysis, we will be depending on the modeling tool as a first step. But how far we are able to incorporate, as if somebody was mentioning before also, how far we are able to model a system very much close to a realistic manner, there only the success relays. Actually, even though we do modeling, and modeling will work fine unless and until we put, so we require a domain knowledge, as you asked me. Surely there is a like we have to train more manpower in this domain, and people also should have a open mind to learn a new domain. And obviously it is a very promising domain for the future applications, because I told you that photonics, because of its wide bandwidth capability, the same system, same module can give even from L band to millimeter wave solutions. So what exactly I wanted to tell you is, we should, as you were telling, I'm facing the problem, like people with, when we are used with the conventional thing, to understand what is the benefit, then only you will be in a better position to appreciate the effort the other person is putting. So what I'm telling, like unless and until we know the advantages or the benefits of using these photonic components for a radar systems or a photonics in a radar system, will not be able to use the tool also in a better way. And if many of the tools, I will tell you from my perspective, I'll see. One is it gives a approximate solution to nearing to the actual situation, but unless and until we know what is the like, we should have the photonics domain expertise as well as the tool knowledge also how to use that. Otherwise, as the previous speaker, Dr. Senthil Kumar was mentioning, people say that it is the limitation of the tool, but I've seen that many of the times, see, many tools, if it is able to provide the third party portability, for example, all the things cannot be expected at the first step when it is a evolving field. So many things I've seen that many of the tools, this especially with the photonic components, they provide a platform where we can interact. There is an interoperability between, for example, I'm just taking, I don't want to specifically name, whichever is not available or the model based designs, we can depend even on MATLAB component as a black box. We can, what exactly I wanted to tell is, it gives third party interoperability features. And another thing is, I'm just trying to tell you that in some cases it is also offering the whatever output we are generating from this, we can have it in a hardware in loop fashion to check whatever components we are having. Whatever is impossible to do it right now with available components, that can be tested. The output generated or output generated out of these models can be reused in our actual systems and try to see the performance. So in nutshell, I don't want to
madam. I will stop you here. I will again start one question from you only, because already we have taken 1 hour of time. So this will be the last round. I will be asking questions because participants are also leaving now. We are already 1 hour late. So one last and very, very targeted question I would like to ask each one of you, that we know that few things still we are doing manually. And when we are doing the things manually or doing the calculations, they are cumbersome process. So I would like to know from each one of you, which is the area in which you want to get rid of those manual calculations or manual testing, and you want to at least incorporate those things in the simulation software. So starting from you, Dr. Meena, I would like to know, suppose given a chance, you are having an option to replace that activity with a simulation software. Because I also know that when we are designing something, some things are there which are still now we don't have any option. But still, if I have a chance to replace that activity with a simulation software, which activity you would like to replace, at least in your domain?
Okay, like I think to some extent the design parameter level entry, we can do it with a simulation software. And I was also mentioning that some of the things which are not able to incorporate in the existing model based designs, some of the tools are offering with the normal interoperability features. And maybe to be, see, ultimately I am just bringing out the point again and again. Our success depends upon whatever be the simulation tool, how far we are able to model to the realistic scenario. For example, in our case, it depends upon, as far as the radar is concerned, it depends if we are able to simulate the effect of, say, atmospheric effects and other on the signal itself, what is echoing back from a target. That manually we are feeding only. Like what I'm wanted to tell you is, suppose if the RCS of the target is more, our signal which is receiving at the receiver will be more. But instead of doing that overall, like what I am telling is, somewhere somebody was mentioning, they offer mission level, component to subsystem, subsystem to mission level. If up to that whole chain of these things can be incorporated in a simulation tool, it will be a best promising solution for entire community.
Thank you, Dr. Meena, for your wonderful perspective. I could understand, because those who are involved in project development, they know that system level realization, how it is difficult. And if we can have from chip to system, everything on simulation tool, nothing like that. Thank you very much. So now I would like to come to Professor Selvaraj. I would like to know what prospects do you believe could we virtualize that are currently completely dependent on physical or hand calculated techniques, at least in your photonics integrated circuits?
We don't do much with hand calculation because there is it's too complex to do.
But some physical
Analytically we do few things, right? But that's just, it's much easier to do. So if it is easier to do back of the envelope calculation, then we better do it that way. I don't want to write a Python code to just do those simple calculations. So if it is simple, keep it simple, and we are not. There is no need to automate that. I think most of the work that we do is primarily with the numerical solvers. So that is taken care. However, I just want to reiterate what Meena was talking about, right? The total system is fine. You can simulate the total system. But then even if you look at simple optical systems, right, you have the optics, and then you have the optoelectronic components as well, right? And even within the optoelectronic components, you have the actual semiconductor part, and then you have the electronics that is integrated with it. So more often what we actually in some of our simulations we do is we interact with semiconductors for optoelectronics, and in the same circuit we have purely photonic processes, right? So there are tools that will talk to each other so that you can take the electric field and then feed it into the semiconductor to look at how the electric field is going to interact with the or optical, electric. When I say electric field, this is electric field of the optical side, and then how it is going to interact with the electrical field that you create in the semiconductor. So these two field integrations and so on, some tools they take care of it. However, there are multiple tools. If one can come up with a platform, right, or a protocol, or an exchange scheme where seamlessly you go from one tool to the other tool, right, without needing to just take only the key parameters and then I feed in. So that is already a filtered, underrated, simulation that I'm going to run through me. So if I can, if we can get a platform, so you have different standards, right? So you can talk to people with different standards. One thing is for layouts, right? If for layouts we use graphical design standards, right? GDS formats, where we can communicate. Similarly, in simulation, if we can think about some standards between different simulation tools, from different vendors, for example, that would be a great addition. So now we can do some wrappers and then do something with it, but I don't want to do it, let's say, right?
Thank you, Professor Selvaraj. I will stop you here. Now I will change the order because you have raised very, very important questions. So Mr. Bhatt, over to you. You have heard how Professor Selvaraj want that seamless change from one simulation tool to the other simulation tool, whether Ansys is having any such platform available, or you are planning to do so?
Yes, definitely. Yes, I heard a couple of comments through this discussion, and yes, so when we are doing the simulation, so there is a question of fidelity and accuracy. So at the initial stages of our system development, we would probably don't care so much about the accuracy. Rather, we would want to run through the simulation quickly to see whether a particular solution is feasible or not. And as we progress through the development, we would want it to be more and more accurate by bringing in all relevant parameters and attributes, pumping them into the simulation, and then getting the more and more accurate results. So this is something that would help us in adopting simulation throughout the development as well as on the verification stage. So typically the V cycle of development, as we talk, I would like the simulation to be deployed, adopted, and used by our customers across the V cycle. Not just because we are a simulation tool vendor, but I truly believe simulation can help advance our research and development and the progress we could make with this country. The second thing, talking about the manpower, the resources, training, etc. Definitely, this is an important area that needs to be addressed. And so we already are doing a lot of knowledge sharing sessions. In fact, if you go today and type in, let's say, Ansys Zemax or say Ansys Numerical, you would find a lot of interesting materials that are freely available to you on YouTube. Not only that, in addition to that, we have Ansys Learning Hub programs, we have Ansys Innovation Space, where we are coming up with plenty of materials to help our customers to understand the domain, to understand the subject. And what's most important here is knowing the tool alone is not really a complete solution. Knowing the tool plus understanding the problem and putting this problem in context is what's most important. And to achieve that objective, we are bringing up a lot of material, helping our customers to see where this problem is relevant and what's relevant in this problem and in which context this problem should be analyzed, so that they will be able to put the tools in the right context as well as the right usage. So these are two important things that I wanted to talk about. And definitely in terms of automation, I probably do not really want to talk too much about that. However, I just want to bring about one example Dr. Senthil Kumar has talked about in his earlier speech. And he said, he was talking about computing the Zernike coefficients or maybe wavefront aberrations, etc. manually, which he himself explained as highly cumbersome, time-consuming, error-prone, etc. Definitely, there are tools like Ansys Zemax solution is very well placed to help us perform these kind of simulations within our tools itself. So with that, I just want to conclude saying that simulation, of course, I don't want to claim that it's a golden bullet that has solutions to every problem. However, I truly believe simulation has the potential to be deployed across the development and verification lifecycle, so that it can truly help us advance the scientific community. That's my belief.
Thank you, Mr. Bhatt. Thank you very much. So I am having now two speakers left, one from defense and one from space domain. So I am slightly becoming greedy. I will stop this question here and I will ask a new question from these two panelists. So Dr. Mandal, you know that aerospace and defense is a highly evolving sector in terms of photonics and optics. Which optical or photonics technology do you believe would be a game changer for the future in aerospace and defense?
Definitely the size and weight minimization. It is a challenge, and in future novel solution we are looking that in future we will have novel solution for this problem. It should be, number of elements should be minimum, it should be lightweight. So few center are working. I know ISRO is working in that domain, in space domain, and from our side also we are trying our best to achieve this goal.
Thank you, Dr. Mandal. Now I will come to Dr. Amitvikram. So, sir, according to you, which technology, especially in optical or photonics technology, is going to be a game changer?
What we feel is the next generation payloads will have to be very high resolution payloads, which require very large optics aperture. Now, these large optics means we have to be it should be lightweighted, the distortion should be minimal while mounting, while in space. So how to minimize this and how to correct for this? There can be segmented mirror approach. Then the precision alignment on board has to be there. There can be developments in active and adaptive optics where using actuators, these can be corrected, these distortions can be corrected. So the way forward can be using high aperture optics for giving high resolutions, with using adaptive and active optics, and sub-aperture testing, as well as very large segmented mirrors. That may be the way ahead, where new challenges need to be taken up for having good payloads.
Thank you, Dr. Amitvikram. I can see a hand raised by Professor Selvaraj. Yes, Professor Selvaraj, you wanted to interrupt and.
Sir, one more thing. Shall I make one more comment? The other question, earlier question.
Please.
Regarding the simulations, we are facing a problem because, as one of my panelists mentioned, see the interchangeability of tools as well as having a common platform for interfacing. Right now we are having a tool for designing the grating, which is a different tool. A tool for designing thin film coatings, which is a different tool. Then having these gratings inserted into ZMAX or Ansys, they won't perform as per the design, because the design has some other aspects also, like a multi-blazing, the angles are different. Then there are some tolerances within the gratings. Similarly, the thin film coatings also. So we want a seamless integration of this in one software with a standardization, as well as the aspects of the design can come into the evaluation. So that was my point in the earlier question.
Yeah, thank you. So I think this is the real pain point, because softwares, they are working in silos. One software to other software, interchangeability and importing and exporting is a really tedious job. So I think I can see the hand raised by Dr. Mandal. Yes, Dr. Mandal, over to you. Just quickly, 1 minute is with you.
Okay, my expectation same like already Dr. Amitvikram already mentioned. Actually, you see, in mechanical domain, there is some standard format through which you can interchange the data, which is not present in optical system, optical software. First thing is this. Second thing is that the present standard simulation software what we are getting are basically that standard is coming, or those coefficients are coming from abroad. All those models are not valid in India. We have our experience shows. So we need Indian context that that atmospheric characteristics, all those to be incorporated in the simulation software, which is missing.
Yeah. So, Mr. Bhatt, so I think you are having a lot of work to be done. And I also agree that whatever models and predictions you are having, maybe mostly from the US and beyond India countries, when we are talking about atmospheric model or propagation model, they should be necessarily from giving the information about Indian atmosphere as well as propagation of details. So just quickly, 1 minute is for you. We have already overshooted our time of 9 o'clock hard stop, but still I would like to give you a chance. Yes.
Sure. Thanks, Punit. Definitely the question of tools interchange, exchanging the information from one tool to other tool is an important question. And we try to develop such kind of collaboration wherever that's possible. And of course, we develop our tools to be compliant with the open collaboration, which means wherever there are industry standards exist, we try to make sure that our tools are compliant to industry standards. And we build the openness in such a way that you can exchange the information from one tool to other tool. For example, even within our Ansys portfolio itself, there are plenty of integrations between the tools to enable not the single physics simulation, rather multi-physics simulation. For example, as we were talking about before, when you perform the optical simulation, you probably want to understand what are the impacts of temperature. So you could perform this coupled analysis from optical to thermal and see what is the effect of thermal effects on top of the optical performance, for example. So this kind of integrated simulation is what we want to achieve. But like rest of the panelists have commented, if the matter comes to some third-party solution and where there is no open standard exists for the information exchange, obviously that would be a challenge, but definitely this is something that we try to address as we move forward. Thank you very much.
Yeah, thank you. I can see one hand also raised by Dr. Meena Desan. So, madam, over to you. Yes.
This is not, I just wanted to know, I also heard that Ansys is working on to give a solution from quantum communication and quantum sensing application perspective, are you planning to launch at the nearby future?
I'm not sure, madam, if you are aware of Ansys numerical solution.
Yes.
So this is a solution where we are trying to approach these new age challenges.
Okay.
Maybe we can approach you and give you more information of this often.
Okay, thank you.
Thank you. Thank you for that question.
So, Professor Salvaraj, you would like to give any closing remarks?
No, nothing specific. I think most of the things are discussed very well. And,
okay, very good. Thank you. I can see hand raised by Dr. Senthil. So, Senthil sir, over to you. Quickly, 1 minute.
Yeah. See, my point is that whatever Mandal or Amit, everyone said, when they are going to seamlessly merge ray tracing and wave propagation, so that whatever IIC professor and other ISRO and DRDO can also merge into that. So that only Ansys can do, so that all software simulations can happen seamlessly. Thank you so much.
We will talk to you, Dr. Senthil. We have solutions to help you in this angle. We will approach you and talk to you about this.
I think the biggest outcome of this panel discussion is everybody wants seamless integration of various tools as well as moving from one side to the other side. And Ansys has to play a big role in that, because you are already working towards digital mission engineering, which I am fully aware, and you are trying to integrate various tools covering various aspects of technology, so that we can, especially in the aerospace, space and defense domain, what all the technologies or simulations, the different verticals are they required. You are trying to integrate, starting from thermal to electrical to even cable coupling, radiation environment, all those things you are trying to cover. But yes, specifically when we are talking about electro-optics as well as photonics domain, I can see is still either if you are having solution, you are not able to reach out to the real experts and explain that you are having a solution, or you are yet to derive those solutions. So I think with this, yeah, please. Someone wanted to tell something? Okay, so I was concluding that yes, we had a very wonderful and interactive roundtable, and I think we got all the important aspects covered under this roundtable, starting from the various work being done by ISRO, DRDO, as well as academic institution in electro-optics as well as photonics domain, and how they are using various simulation tools, how simulation tools are helping in their overall design realization cycle, and how they are reducing the time from conceptualization to the delivery of the hardware. And yet the overall outcome has come that yes, we are getting help from these simulation tool, but still lot to be done, mostly in the system point of view, because we are having simulation tool to solve one problem to other problem to the third problem, but there is no simulation tool exist which solves most of the problems, and that is the real problem all designers are facing. And I think action is now on software tool designers like Ansys to provide the solution for that. With this closing remark, I would like to thank each one of you. I can see from last 4.5 hours, we are still on this platform, which is very rare. Mostly online platforms, nobody will stay for more than 90 minutes, but still we are having almost 50 delegates. We started with 150 almost, and then we are having a very good attendance, and you are having in chat box to share your feedback. So those who are still attending, kindly provide the feedback about all our program. And yes, now I am confident that very soon we are going to have another session on aerospace and defense, especially with this quantum technologies, because we never thought that these many people will be interested in this particular technology. But yes, people are there, and this is a very, very emerging field, and government of India has a very huge, our Director SAC has told 8,000 crores project on this quantum frontiers, in which ISRO, DRDO, ISC and all, most of the research and development organizations, they are working. And I hope with this program, we would have done some justice to each one of you, those who have attended, to learn and understand the intricacies of electro-optic system as well as photonic system. With this word, I would like to conclude this session. Thank you very much for joining us and staying with us and providing your wonderful perspective. Dr. Meena, Mr. Bhatt, Dr. Senthil Kumar, Professor Selvaraj, and Dr. Mandal. And last but not the least, Mr. Amitvikram Kurulkar, and the entire organizing team. And we are always missing when I'm talking about IEEE MTT, AP Bangalore Chapter and AESS. But yes, Ansys is also equal partner in organizing this. So thank you very much for joining our hands and making this program a huge success.
Thank you, Puneet, for a wonderful discussion. Thank you. Thank you all.
Thank you. Thank you, sir.
Have a good evening.
Thank you. Good night.
Good night.
Good night.